You are listening to Event Sourcing Unveiled, navigating common pitfalls and building resilient systems. Like and subscribe to keep up to date on our latest audiobooks. Event Sourcing Unveiled, navigating common pitfalls and building resilient systems. Chapter 1, The Promise and Peril of Event Sourcing. The lure of event sourcing. In the digital age, businesses are awash in data. Every click, every transaction, every interaction leaves a digital footprint. We strive to build sophisticated systems capable of processing this deluge, aiming for robust, scalable applications that can adapt to ever-changing demands. Amidst this technical landscape, a compelling architectural paradigm known as event sourcing has emerged, promising a powerful new way to manage data and build exceptionally resilient systems. The appeal of event sourcing is, at first glance, remarkably strong. Imagine a system that, instead of just storing the current state of things, meticulously records every change that has ever taken place. Think of it like an ultimate, immutable ledger, a comprehensive and perfectly ordered history of your entire application. This complete historical record grants developers and businesses extraordinary auditability. You can literally trace every step that led to the current situation, offering unparalleled transparency and traceability. For regulatory compliance, fraud detection, or simply understanding complex user behavior, this capability is a goldmine. Beyond auditability, event sourcing offers the intriguing capability of time travel debugging. If a bug manifests in your live system today, you can rewind the sequence of events to a precise moment in the past, reconstruct the system's state exactly as it was then, and step through the process that led to the error. This temporal query power isn't just for debugging. It enables sophisticated historical analysis, drives business intelligence, and even allows for the reprocessing of past events with new rules, essentially letting your business travel through time to gain deeper insights or adjust to new requirements. At its heart, event sourcing embodies a deeply domain-centric approach. Instead of merely thinking about tables and rows of data, you model your system around the events that genuinely occur in your business domain, the things that truly matter to the business, like order placed, item added to cart, or account credited. These events become the first-class citizens of your architecture, driving system behavior and evolving in close alignment with your business logic. This perspective actively fosters a much richer and more accurate understanding of the domain itself. Furthermore, when strategically paired with architectural patterns like Command Query Responsibility Segregation, CQRS, event sourcing can unlock significant benefits in terms of scalability and decoupling. The right model, where events are generated, can be completely separated from multiple read models, optimized views for querying, allowing each to scale independently. The stream of events flowing through your system also serves as a powerful, loosely coupled messaging mechanism, enabling different parts of your application to react to changes without rigid dependencies. To illustrate, consider a simple bank account. A traditional database might only store your current balance, $1,500. If you then ask, "How did I arrive at this balance?" the database on its own cannot tell you directly. It only knows the latest aggregated state. Now, imagine a system that records every single transaction: account created, initial balance, $0, deposit made, $1,000, withdrawal made, $200, deposit made, $700, fee charged, $50. With this complete event history, your current balance is still accurately calculated as $1,500. But crucially, you can now answer questions like, when did my balance first exceed $500? Or, what was my balance on the 15th of last month? Or, show me all transactions greater than $500. Event sourcing is precisely this transformative shift in mindset, from merely storing the current state to storing the immutable stream of events that led to that state. What is event sourcing? A quick primer. Before we delve into where things can quickly go awry, let's establish a common understanding of the fundamental components of event sourcing. This section provides a brief refresher, not a deep dive into the pattern itself, simply to ensure we're all aligned on the terminology and core concepts we'll discuss throughout the book. At its very core, event sourcing revolves around 5 key components: events, These are the heart of event sourcing. An event is a record of something that has occurred in the past. It is an immutable, past-tense fact about your domain. For instance, in an e-commerce system, order placed, payment received, item shipped, and product returned are all prime examples of events. They are critical because they precisely define the business actions and changes that have transpired. Once an event is recorded, it permanently exists. It never changes or disappears. It forever marks a specific moment in time when a definite thing happened. Event store. This is the specialized storage mechanism for your events. Unlike a traditional database that stores the latest state, an event store is an append-only log. This fundamental characteristic means you can only add new events to the end of the stream. You never modify or delete existing events. This immutability is foundational to the integrity, auditability, and temporal querying capabilities of an event source system. Each event is stored with a unique identifier and frequently a timestamp, diligently maintaining the precise chronological order of occurrences. Aggregates. In the context of event sourcing, an aggregate is a cluster of domain objects that are treated as a single, consistent unit for data changes. It represents the consistency boundary for your system's write model. When a command, an intention to change state, enters the system, it's typically directed at an aggregate. The aggregate then reconstructs its current state by replaying its historical events, applies the new command, and if valid, emits new events that are then persisted to the event store. An aggregate's primary responsibility is to ensure that strict business rules, often called invariants, are never violated within its boundary. A classic example is an order aggregate, which might contain line items and shipping details. All changes related to a single specific order would exclusively go through this order aggregate. Projections, read models. Because the event store is an append-only log, it's not inherently optimized for direct, fast querying of the current state. If you need to quickly display a user's profile, retrieve a list of active orders, or generate a complex report, replaying all events every time would be extremely inefficient. This is precisely where projections, or read models, become indispensable. A projection is a materialized, often denormalized view of your data, specifically optimized for particular queries or user interface displays. These projections are built by consuming the continuous stream of events from the event store and updating a more traditional, query-friendly database, which could be a relational database, a NoSQL document store, or even an in-memory cache. For example, events like order placed and item added to order might be consumed to build an active orders projection, showing just the essential details for display on a dashboard. Commands. While not strictly part of event sourcing's core event storage mechanism, commands are integral to how your system interacts with aggregates. A command represents an intent to perform an action or change state, e.g., place order, add item to cart. Commands are processed by your application logic, which then instructs aggregates to perform actions, which in turn might produce new events. The typical flow for writing data in an event-sourced system looks something like this. A user sends a command, e.g., add a book to my cart. This command is received and processed by an application service, which loads the relevant aggregate, e.g., the specific shopping cart instance, by replaying its past events from the event store. The aggregate then determines if the command is valid given its current internal state. If validated as legitimate, the aggregate applies the change and generates new events, e.g., book added to cart. These newly generated events are then atomically appended to the event store. For reading data, the flow is distinct. Events from the event store are continuously streamed and used to asynchronously update one or more specialized projections, read models. When a user needs information, e.g., show me my current shopping cart, a query is issued directly against the appropriate projection, which, by design, is optimized for fast read operations. This inherent separation of write operations, handled by aggregates and the event store, and read operations, handled by projections, is a powerful aspect of event sourcing, commonly referred to as CQRS. The unspoken truth, why event sourcing goes wrong. The concepts outlined above paint an undeniably elegant and incredibly powerful architectural picture. Many online resources and introductory materials often stop here, focusing solely on the manifold benefits. This frequently leads to an initial surge of enthusiasm, an aha moment where developers and architects believe they've discovered the ultimate silver bullet for their intricate system design challenges. However, quite often, this triumphant aha moment quickly, and rather uncomfortably, transforms into an uh-oh. As teams transition from theoretical understanding to concrete implementation. Event sourcing, despite its theoretical elegance and potent advantages, introduces a unique set of complexities and challenges that can disproportionately overwhelm development teams and seriously derail projects if not thoroughly understood and meticulously managed. It is unequivocally not a silver bullet, nor is it a universal solution applicable to all problems. Rather, it's a highly specialized and powerful tool, capable of delivering astonishing results in the hands of skilled practitioners for the right problems, but holding the very real potential for disaster when misapplied or poorly implemented. The shift in architectural complexity is profound. Instead of primarily contending with the intricacies of relational database schemas, transactions, and explicit state management found in traditional CRUD, create, read, update, delete, systems, you are charged with managing. Complexity shift. The fundamental problem of managing a system's current state is subtly transformed into the more nuanced challenge of managing the integrity, consistency, and ongoing evolution of an immutable stream of events. This demands a significantly different mental model, new paradigms for thinking about data lifecycle, and fresh approaches to implementing business logic. Handling change over time, schema evolution. What happens when the precise definition or structure of an event organically needs to change? For instance, if an order-placed event initially only included a customer identifier, but later absolutely requires the customer's full shipping address. Crucially, you cannot simply alter historical, immutable events within an append-only log. This challenge, known as schema versioning or event evolution, is deceptively difficult to get right and represents a very common and agonizing source of pain for teams. Debugging and testing in a temporal system. Debugging an event-sourced system is not just about inspecting the current state of a database table. You inherently need to understand the precise sequence of events that precisely led to that state. Replaying events, meticulously dealing with asynchronous projection updates, and ensuring eventual consistency across myriad different read models introduce entirely new layers of complexity to both testing and diagnostics. The traditional breakpoint and inspect approach, while still useful, often proves insufficient on its own. Operational overhead. Running an event-sourced system reliably in production brings its own distinct set of operational challenges. Managing a highly available and scalable event store, ensuring robust and guaranteed event delivery, proactively monitoring the health of numerous event streams versus mere application process health, handling comprehensive backups, and performing intricate disaster recovery procedures all necessitate specialized knowledge, refined processes, and often bespoke tooling. Rebuilding projections, particularly for very large or complex datasets, can be an extremely time-consuming and system-impacting operation. Misunderstanding core concepts. Perhaps the most insidious and damaging pitfall is a fundamental misunderstanding or misapplication of event sourcing's core, foundational concepts. Misinterpreting what truly constitutes a good event, designing incorrect or leaky aggregate boundaries, or failing to grasp the profound implications of eventual consistency can lead directly to fragile, overwhelmingly hard-to-maintain systems that, ironically, offer none of the promised benefits and all of the headaches. Furthermore, attempting to forcibly apply event sourcing to a problem domain where it simply does not fit is a common and costly form of overengineering that invariably saps resources, erodes team morale, and often leads to project failure. Consider event sourcing akin to a precision-engineered, high-performance race car. In the hands of a supremely skilled driver on a perfectly optimized track, it can achieve truly incredible performance, speed, and agility. However, attempting to navigate that same race car in the hands of an inexperienced driver on a bumpy, unpaved back road will almost inevitably lead to a catastrophic crash, leaving behind a trail of profound frustration and financial disappointment. Event sourcing is undeniably a powerful tool, capable of building astonishingly robust systems. But it demands skill, profound understanding, and extremely careful consideration to proactively avoid constructing what could easily become a brittle house of cards. What this book aims to achieve. This book is born from the critical recognition that while a substantial volume has been written about the transformative benefits of event sourcing, significantly less attention has been rigorously dedicated to its considerable architectural, developmental, and operational complexities. This book aims decisively to fill that crucial gap. Our primary, overarching goal is to demystify the common pitfalls and prevalent mistakes that development teams consistently encounter when undertaking event sourcing implementations. We will move beyond the superficial, high-level discussions and plunge deep into the specific, intricate challenges that frequently cause promising projects to falter or outright fail. For each identified pitfall, we will thoroughly explore the symptoms. How does this particular problem manifest itself within your system? What are the observable signs that something is amiss? The root causes. Why does this problem genuinely occur? What underlying architectural or conceptual misunderstandings lead directly to its emergence? Practical solutions. What concrete strategies, established patterns, and disciplined best practices can you immediately apply to either proactively avoid or effectively resolve the issue? By providing this practical, solutions-oriented, and actionable guidance, we aim to equip you with the essential knowledge required to make profoundly informed decisions throughout your event sourcing journey. Whether you are considering event sourcing for a brand new project and genuinely wish to understand its true, nuanced complexities upfront, just starting out with event sourcing and are keen to avoid the common beginner traps and early missteps, struggling with an existing event sourcing implementation that has, for various reasons, become difficult to manage, maintain, or evolve. This book will serve as your essential and trusted guide to successfully building resilient, scalable, and genuinely maintainable event-sourced systems. We will meticulously focus on clear explanations, highly relatable examples, and directly actionable advice, ensuring the content remains broadly accessible even if you do not possess a deep, prior background in distributed systems or intricate domain-driven design. Navigating the journey ahead. Your journey through this book will systematically take you through the various stages and core components of an event-sourced system, meticulously dissecting precisely where common errors and pitfalls tend to occur. In Chapter 2, we will diligently revisit the very core concept of an event, as it becomes abundantly clear that many subsequent architectural and operational mistakes directly stem from a fuzzy or incomplete understanding of what a true event genuinely is. Chapter 3 will deeply dive into the crucially important topic of aggregates and meticulously examine the typical design blunders that invariably undermine systemic consistency. Chapter 4 will comprehensively tackle the ubiquitous challenges associated with projections and read models, a well-known and frequent source of performance issues and lurking data inconsistencies. Chapter 5 will directly address the dreaded schema versioning nightmare, the complex and often painful process of how to gracefully evolve your event definitions over extended periods of time without inadvertently breaking your entire system. Chapter 6 will equip you with the necessary tools and insights to confidently navigate the temporal labyrinth inherent in debugging and rigorously testing intricate event-sourced systems. Chapter 7 will thoroughly explore the often overlooked operational overdrive involved in the robust deployment, continuous monitoring, and reliable recovery of event-sourced applications in production environments. Chapter 8 will shine a critical light on insidious performance pitfalls and precisely how to maintain optimal system speed and responsiveness as your event streams inevitably grow to gargantuan sizes. Chapter 9 will assist you in confronting the crucial, when not to conundrum, helping you to accurately identify scenarios where applying event sourcing might constitute destructive overengineering, and simpler solutions would unequivocally suffice. Chapter 10 will investigate the often neglected people and process side of implementing event sourcing, specifically addressing the significant organizational and cultural challenges associated with its successful adoption. Chapter 11 will provide concrete strategies for repairing the damage when things inevitably go wrong, offering tangible recovery techniques and consolidating all the essential best practices discussed throughout the book. Finally, Chapter 12 will offer a concise yet insightful look at the future trajectory of event sourcing and strongly emphasize the paramount importance of continuous learning and active community involvement. Embarking on an event sourcing journey represents a significant architectural undertaking, but with the correct knowledge, a thorough understanding of potential pitfalls, and a disciplined approach, it can truly unlock tremendous power, unprecedented flexibility, and profound resilience for your applications. This book is crafted to be your indispensable companion on that transformative journey. Chapter 2, Back to Basics, Re-understanding the Event. The event, the immutable heart of event sourcing. At the very core of event sourcing lies the concept of an event. As we touched upon in Chapter 1, an event signifies something that has occurred within your business domain. It's an immutable, undeniable fact from the past, a cornerstone upon which your entire event-sourced system is meticulously built. If you misinterpret the definition and modeling of your events, it's akin to constructing a magnificent house on shifting sand. The subsequent structures, no matter how impeccably well designed, will inevitably prove unstable and eventually crumble. Many of the most common and frustrating pitfalls encountered in event sourcing can be directly traced back to a fundamental misunderstanding or a precise misapplication of what a true event genuinely is. So, what truly makes a good event in the context of event sourcing? This chapter will delve deeply into common mistakes frequently made when defining events and will meticulously guide you towards creating events that are clear, potent, resilient to future change, and serve as a robust foundation for your system. Pitfall 1. Events as data transfers versus domain facts. One of the most insidious and pervasive pitfalls is the tendency to treat events as merely a mechanism to transfer raw data or as a simple representation of current state, rather than recognizing them as concrete, immutable facts about something significant that has already happened. Symptoms: lack of clear meaning. Your events might bear generic names lacking specific business intent, such as order updated, user changed, product modified. These labels fail to convey what specifically occurred, merely indicating that something was altered. Resemble database rows API payloads. The payload or data content of these events often mirrors every field of an entity, even those completely unaffected by the specific change. This frequently resembles a snapshot of the current state of an entity, instead of containing only the highly relevant information directly pertaining to the past occurrence. Generic data buckets. Events devolve into large, amorphous data structures, inherently difficult to comprehend at a glance, and challenging for other parts of the system to specifically react to in a precise, targeted manner. Root cause. This pitfall commonly originates from a traditional CRUD, create, read, update, delete mindset. In a typical CRUD system, your primary focus revolves around constantly updating records within a database to reflect the latest state. When transitioning to event sourcing, teams sometimes mistakenly map these update operations directly to events, inadvertently losing the crucial nuance of a domain event. Instead of merely thinking, this data field changed, the correct paradigm shift requires you to think, this specific action happened, which consequentially resulted in a change. The focus fundamentally shifts from the static data itself to the intent behind the action and the consequence of that significant occurrence. Solution: focus on past tense, business language, and intent. A paramount principle of event sourcing is that events unequivocally describe what has happened, not what should overtly happen or what is the current state. To effectively counteract this pitfall, you must wholeheartedly embrace the following guidelines. Naming convention. Events must invariably be named in the past tense and reflect a business-centric verb followed by a meaningful noun. A widely adopted and effective structure is noun past tense. Bad example: update order, this sounds like a command, not an event. Order changed, this is far too generic and vague. Good examples: order placed, item added to cart, payment received, shipping address updated, customer credit limit exceeded. Observe how these names clearly and succinctly state a factual historical occurrence. Use business language. The names and the internal content of your events should consistently resonate with your domain experts and business users. If your business team struggles to understand what product state transitioned conceptually means, it is highly probable that it is a poorly chosen and ineffective event name. Strive for crystal clear communication and the pervasive use of ubiquitous language. Content, minimal and focused. The payload of an event should judiciously include only the data that is directly relevant to that specific occurrence. It must provide sufficient context to comprehend what happened and why it mattered, but emphatically not a full snapshot of the entire aggregate state. Bad example, for order shipping address updated. An event containing the entire order object, encompassing all its items, prices, historical addresses, and so forth. This is excessive and unfocused. Good example, for order shipping address updated. An event containing ordered, old address, new address, and potentially updated by user. This provides concise, highly relevant information describing precisely the specific change that occurred, nothing more, nothing less. Analogy. Consider an event as analogous to a concise newspaper headline. Local store declares bankruptcy. A well-crafted headline is factual, presented in the past tense, and directly informs you precisely what happened. It does not and should not include the store's full financial history, every last item in its inventory, or the detailed life story of its owner. Similarly, order created is a clear, precise headline for a significant business fact. In contrast, a vague order updated is akin to a meaningless headline, store changed, which fails to impart any specific or actionable information. Pitfall 2. Overly granular events, the micro-event trap. On the diametrically opposite side of the spectrum from generic events lies the equally problematic mistake of making events excessively granular, leading to the generation of a deluge of minuscule, atomic events for every single, minute data alteration. Symptoms: bloated event streams. A single, seemingly logical business action results in a disproportionately large multitude of events. For instance, updating a customer profile might inadvertently trigger customer name changed, customer email changed, customer phone number changed, and customer address, line 1 changed, all as separate events occurring practically simultaneously. Increased complexity. Aggregates and their corresponding projections become heavily burdened with the responsibility of handling an excessive number of extremely specific events. This leads to verbose, convoluted event handlers that are progressively difficult to maintain and understand. Performance overhead. While not always immediately crippling, a massive proliferation of tiny events can cumulatively lead to considerably increased storage requirements and potentially slower aggregate reconstruction times due to the sheer volume of events needing replay. Difficulty in understanding. When attempting to audit or comprehend an event stream in its entirety, it becomes exceptionally challenging to discern the overarching, higher-level business action amidst the overwhelming noise of microscopic, individual data changes. Root cause. This particular trap often originates from an exaggerated interpretation of the principle of immutability and an almost obsessive desire to meticulously capture every single conceivable change. Teams might erroneously conclude, since events are immutable, I am compelled to record every solitary field alteration as its own distinct event. This can also arise from a profound fear of losing information if a very-minute change isn't meticulously documented with its own dedicated event. Occasionally, it's simply a profound lack of understanding regarding what truly constitutes a meaningful business change versus a mere, trivial, underlying data field alteration. Solution: embrace business-level events and consistency boundaries. The pivotal remedy for this pitfall is to meticulously define an event at the level of a meaningful business change, an occurrence that other clients or external systems might genuinely desire or need to react to. Meaningful business change. An event should unequivocally represent a significant impact or an outcome that possesses a distinct, tangible business significance within your domain. Does the business genuinely care or need to react differently? If address line 1 was subtly altered versus address line 2, Or does the business primarily concern itself with the fact that the shipping address as a whole was definitively updated? Typically, it is the latter. Context is key. Always consider the broader business context surrounding the change. If a user comprehensively updates their entire contact information through a single form submission, and the business inherently views this as one unified, logical update to their contact details, then a single, consolidated customer contact info updated event, which thoughtfully contains all the relevant updated fields, might be far more appropriate than attempting to fragment it into numerous individual, field-level events. Event storming. This highly effective and collaborative workshop technique, where domain experts and technical staff cooperatively define a system by rigorously modeling its core events, proves invaluable here. It fundamentally assists in identifying the true, meaningful domain events that genuinely matter to the business, thereby effectively separating critical signal from mere noise. Example: instead of separate product price changed, product description changed, and product weight changed events, you might design a single, consolidated product details updated event if all these individual changes typically occur as a single, cohesive logical unit from a business perspective. However, if a price change specifically triggers a distinct discount recalculation, whereas a description change does not, then separate, discrete events, product price changed, product description changed, would be significantly more appropriate, allowing downstream systems to react precisely to each distinct business impact. The nuance here is absolutely crucial. The correct choice intrinsically depends on your specific domain and its unique underlying invariance. Pitfall 3. Overly broad events, the macro event blob. At the complete opposite end of the spectrum from overly granular events, we encounter events that are excessively broad, attempting to encapsulate multiple disparate business changes or carrying an inordinate amount of, sometimes completely unrelated, information within their payloads. This is the macro event trap. Symptoms: lack of precision. An event with an overly generic name like order processed or user action performed inherently fails to convey sufficient specific information. What kind of user action was performed? How, precisely, was the order processed? The ambiguity causes confusion. Difficult for consumers. Systems attempting to consume these broad events genuinely struggle to react precisely or efficiently. They are often forced to excessively inspect the event's bloated payload to deduce which particular part of the broad event is relevant to their specific concerns, frequently leading to overly complex, conditional logic. Hard to evolve. If you later need to add a single new piece of data or subtly refine one small aspect of a broad event's meaning, you might inadvertently introduce breaking changes or unintended impacts on a multitude of different consumers, as the event is treated as a single, monolithic contract, masking multiple business operations. A single, nebulous macro event might inadvertently represent what should logically be decomposed into 2 or 3 distinctly separate business events that occur as sequential results of a single command. Root cause. This particular pitfall frequently occurs due to a misguided impulse to oversimplify the event model or a profound lack of deep, comprehensive domain understanding. Instead of painstakingly identifying the truly distinct facts that collectively constitute a complex operational sequence, everything is cursorily bundled into one oversized event. It can also stem from a deliberate, though misguided, attempt to model the current state of an entity directly within an event, which fundamentally misses the core purpose of events as immutable historical facts. Solution: identify distinct business concepts and their consequences. The effective solution is to rigorously decompose broad, ambiguous operations into their fundamental, distinct business facts. Distinct business fact. Each event should unequivocally describe one, and only one, atomic business fact or occurrence. If a change or event payload can logically be broken down into multiple, independently meaningful occurrences, then it should, in all likelihood, be split into separate events. Focus on consequences. Critically consider the downstream implications or consequences of the event. If order processed genuinely embodies payment received and order dispatched, these are demonstrably 2 distinct business facts with potentially very different downstream consequences. E.g., payment receipt triggers financial accounting updates, whereas order dispatch triggers shipping notifications. Separating them allows different, specialized downstream systems to react precisely and specifically to what they uniquely care about. Example: instead of a single, all-encompassing user account updated event that could implicitly mean a password has changed, an email address was updated, or a profile picture was altered, you should design distinct events like user password changed, user email changed, and user profile picture updated. Each of these individual events represents a distinct factual occurrence with its own unique and direct business implications. Analogy: imagine a news reporter attempting to summarize an entire day's worth of complex events in a single, impossibly long sentence, rather than providing distinct headlines and separate articles for each individual significant story. While a broad order-processed event might seem convenient on the surface, it ultimately obscures the actual, granular narrative of your complex system. Pitfall 4. Relying on event order for business logic, implicit ordering. Another subtle but profoundly dangerous pitfall occurs when business logic, either subtly or explicitly, assumes a very specific global order of events within the entire system, even when that precise order isn't strictly necessary for the business logic or cannot be reliably guaranteed in a distributed, asynchronous environment. Symptoms: fragile system. The application exhibits incorrect behavior or critical failures if events arrive slightly out of their assumed order, a common occurrence in distributed messaging systems, or if a specific, expected event is unexpectedly skipped. Hard to refactor. Introducing new parallel processing capabilities or deliberately changing the logical order of non-dependent operations becomes exceedingly difficult without necessitating a significant rewrite of large portions of the system's logic. Hidden dependencies. Core business rules are not explicitly modeled within the code. Instead, they implicitly rely on the exact temporal sequence of events within the broader event stream. Root cause. This pitfall frequently arises from thinking of the event stream as a perfectly linear, globally ordered transaction log, much like in a traditional single-node database. While events within a single, specific aggregate stream are inherently and strictly ordered, because they represent the sequence of changes to that aggregate, their precise order across different aggregates or in the grand, global event stream might not rigorously adhere to what you implicitly assume. This global order can be subject to unpredictable network latency, message broker characteristics, and the inherent concurrency of distributed systems. Solution: explicitly model dependencies and use aggregate versioning. Business logic on aggregate state. Core business logic should primarily operate on the aggregate's precisely reconstructed state and its internal version, not solely on the assumption of a strict global event order. When an aggregate processes a new incoming command, it validates that command against its current internal state, meticulously reconstructed from its own historical event log. This ensures consistency within that aggregate. Concurrency control, versioning. Leverage aggregate versions to ensure robust, optimistic concurrency. Every time an aggregate successfully applies a command and emits new events, its version number must monotonically increment. When an application loads an aggregate for modification, its current version is obtained. The command requesting the change must include this expected version. If the version provided in the command does not precisely match the event store's latest version for that aggregate instance, it signifies that another change occurred concurrently for that same aggregate. The command is then rejected, actively preventing lost updates. Idempotency for consumers. While aggregates rigorously handle transactional consistency for their own state, projections, and other downstream event consumers must be idempotent. This critical characteristic means that processing an event multiple times should produce the exact same result in the consumer as processing it once. This makes your system inherently resilient to duplicate event deliveries, which are a common occurrence in distributed messaging systems that typically guarantee, at least once, delivery. Analogy: imagine a complex recipe. A well-written recipe, like a well-designed event source system, provides clear instructions like add salt after the water boils and stir until dissolved. It does not, however, contain arbitrary instructions like wait for the phone to ring, then stand on one leg, then add salt. In event sourcing, the aggregate strictly ensures its internal sequence of steps is correct and ordered. But the broader dance of many different, concurrently operating aggregates across the system might not be a perfectly choreographed line dance, with a global, guaranteed temporal sequence of every movement. Best practices for defining events. To help you proactively avoid these common pitfalls and ensure your events truly form a robust, reliable foundation for your event sourcing implementation, diligently consider and apply these best practices. Domain event storming. This highly recommended collaborative workshop involves bringing together domain experts, developers, and other key stakeholders to visually map out the complex business process, identify clear commands, and most importantly, collectively discover the true domain events that inherently drive the system. It is exceptionally effective at building a shared understanding and ensures your events accurately reflect genuine, concrete business facts. Use business language. Consistently name your events and the fields within their payloads using the precise, ubiquitous language of your domain. This practice significantly improves inter-team communication, drastically reduces ambiguity, and ensures that your technical model remains in close alignment with your underlying business reality. Immutability above all. Once an event has been meticulously written to the event store, it should, under no circumstances, ever be changed or deleted. This principle is absolutely fundamental to the unimpeachable auditability, historical integrity, and reliability of event sourcing. Any perceived change to past information should result in a new compensating event. Atomicity within a business fact. An event should unambiguously describe a single, atomic business fact or occurrence. If a logical change can be naturally broken down into smaller, independently meaningful facts, consider modeling them as distinct events. Minimal data. Rigorously include only the specific data absolutely necessary to convey precisely what happened and to provide crucial context for consumers to react effectively. Avoid the common temptation to stuff an entire aggregate's current state into every single event. This practice keeps event payloads lean, minimizes storage requirements, and significantly simplifies future schema evolution. Avoid technical jargon. Ensure both your event names and the data within their payloads remain squarely business-centric and easily understandable by non-technical stakeholders. Avoid using overly technical terms like ID, prefer orderid, customerid, generic status, use order status, or arcane system-specific codes where clear, concise business terms are available and more appropriate. Chapter summary. Events are not merely static data records. They are the fundamental, immutable facts that meticulously narrate your business's dynamic history. A clear, precisely defined event strategy is absolutely paramount to the enduring success of any event sourcing implementation. Misinterpreting events as simple data transfers, making them either excessively granular or overly broad, or implicitly relying on an unguaranteed global ordering, are pervasive yet dangerous traps that can irrevocably lead to systems that are complex, inherently fragile, and excruciatingly difficult to maintain. By diligently focusing on events as past tense, business-centric facts that describe single, meaningful changes, and by meticulously defining their precise scope and exact content, you lay a profoundly solid and resilient foundation for your entire system. Investing dedicated time in collaborative techniques like event storming will significantly help ensure that your events accurately align with your true business reality and progressively become the highly resilient building blocks of your system's architecture. This discipline, though initially challenging and requiring a paradigm shift, will proactively prevent cascading issues and save an immense amount of effort and resources in the long run. Chapter 3. The Aggregate Abyss. Common design mistakes. Aggregates, the guardians of consistency. If events are the indelible facts meticulously recording your system's history in event sourcing, then aggregates stand as the unwavering guardians of its consistency. An aggregate is far more than a mere data entity. It is a pivotal concept in domain-driven design, DDD, that delineates a cluster of domain objects treated as a single, indivisible unit for any data changes. Crucially, an aggregate fundamentally serves as a consistency boundary for your system's right model. This implies that any business rule, or invariant, that absolutely must hold true after a single atomic operation is enforced entirely within the immutable confines of a specific aggregate instance. All modifications to the data residing within an aggregate must exclusively traverse through its designated aggregate root. If these critical aggregate boundaries are designed incorrectly, you run a severe risk of encountering data corruption, persistent inconsistent states, and constructing a system that is inherently brittle and overwhelmingly difficult to manage or evolve. This chapter will meticulously explore the prevalent pitfalls in aggregate design, providing precise guidance on how to define their boundaries and manage their interactions correctly, thereby enabling you to build truly robust event source systems. Pitfall 1: Incorrect aggregate boundaries, too big, too small. One of the most frequent and profoundly impactful mistakes in event sourcing is the incorrect definition of aggregate boundaries. This critical error typically manifests itself in two diametrically opposing ways: aggregates that are designed to be far too large, or aggregates that are designed to be far too small for their consistency needs. Symptoms: too big, the God aggregate. High contention. A single, excessively large aggregate attempts to control too many disparate concepts, e.g., encompassing an entire shopping cart system, comprehensive customer management, inventory control, all within one aggregate. This leads to scenarios where many different commands, potentially originating from various parts of your system, constantly attempt to update this single, large aggregate concurrently. This results in frequent optimistic concurrency conflicts, where legitimate updates are consistently rejected because the aggregate's version has changed in the interim. Consequently, users experience frustrating "please try again" messages, eroding usability. Performance bottlenecks. Reconstructing the current state of a very large God aggregate might necessitate replaying an enormous number of historical events. This process can become excruciatingly slow and inefficient, especially for aggregates that possess very long lifespans or accumulate vast event histories. Loss of domain clarity. A God aggregate attempts to manage an excessive number of unrelated business concepts, making it exceptionally challenging to ascertain its true responsibilities or precisely what specific invariants it is genuinely supposed to protect. This obscurity hinders shared understanding and maintainability. Scaling difficulties. A monolithic, overly large aggregate invariably becomes a significant bottleneck for overall system scalability, as it fundamentally represents a single, highly contended point of write operations. Too small, multiple microaggregates for a single consistency concern. Broken business invariants. Related business rules that must be enforced atomically are inadvertently fragmented and spread across multiple, independent aggregates that cannot inherently guarantee atomic changes. For example, if checking an account balance and debiting funds from it are handled by separate aggregates, it becomes practically impossible to reliably prevent an overdraft situation. Distributed transaction trap. Teams mistakenly attempt to achieve atomicity across these small, decoupled aggregates by implementing complex distributed transaction mechanisms, such as two-phase commits. These paradigms are generally considered an anti-pattern in event sourcing and distributed systems, leading to increased fragility. Data inconsistencies. Without robust and guaranteed consistency for interrelated operations that span these small aggregates, the system can regrettably end up in persistently inconsistent states, leading to data integrity issues. Root cause: too big. Frequently, this arises from an inability to accurately identify the true boundaries of transactional consistency within the domain. There's a common tendency to mistakenly conflate a bounded context, which is a logical boundary for a subdomain in domain-driven design, with a single, massive aggregate. Furthermore, a resistance to genuinely embrace eventual consistency for cross-aggregate operations inadvertently pushes teams to cram far too much transactional logic into one behemoth aggregate. Too small. This can be inadvertently fueled by an overzealous adoption of microservices principles, where every single entity is mistakenly conceptualized as its own aggregate, without adequately considering the actual, underlying consistency requirements. The crucial insight that is often missed here is that an aggregate fundamentally defines a consistency boundary, not merely an individual entity. Solution: identify invariants and adhere to the single right model principle. The effective antidote to incorrect aggregate boundaries lies in deeply understanding your domain's invariants and strictly adhering to the single right model principle. Identify invariants. What are the absolutely critical business rules that must always be true within a single, atomic business operation? These specific, non-negotiable rules precisely define the appropriate boundaries of your aggregates. For example, in a banking system, the invariant, an account's balance must never go below zero, means that both the explicit check for sufficient funds and the subsequent debiting of funds must occur within the same aggregate instance, a specific bank account aggregate, to guarantee its enforcement. Another example: a customer's shopping cart total must not exceed their available credit limit. If shopping cart and customer credit limit are distinct aggregates, enforcing this particular invariant requires a different, more complex strategy, typically a saga, which will be discussed in the next pitfall. Single right model principle. A foundational tenet of event sourcing is that only one aggregate instance should be directly modified as a comprehensive result of a single command. If a command appears to update multiple aggregates simultaneously, it is a strong and clear indicator that either your existing aggregate boundaries are incorrectly defined, pointing to one of the too big or too small issues we just discussed. You are, in fact, dealing with a complex, multi-step business process that inherently spans multiple consistency boundaries, which consequently requires eventual consistency and a sophisticated coordinating mechanism like a saga or process manager. Case study example: order placement versus inventory management. Consider a typical e-commerce system where a customer places an order. This business process inherently involves both an order aggregate identified by, for instance, orderid 123, and multiple inventory item aggregates, each identified by, perhaps, producted, ABC producted, XYZ for the items in the order. Pitfall: attempting to decrement inventory levels directly within the order aggregate. If the order aggregate attempts to manage global inventory levels, it effectively becomes a God aggregate. Many concurrent orders would simultaneously attempt to update the same inventory items, leading to pervasive contention and frequent write failures. Correct design: the order aggregate is solely responsible for the consistent state of that specific order. Inventory management is a distinct business concern, rigorously managed by separate inventory item aggregates, each ensuring its own stock level consistently remains above zero. Placing an order, in this design, initiates a broader process that logically involves both the order and inventory aggregates. This naturally leads us directly to our next critical pitfall. Pitfall 2. Transactions spanning multiple aggregates, the distributed transaction trap. Following directly from the aggregate boundary issue, a common and highly problematic pitfall is the attempt to achieve atomicity for operations that inherently span multiple distinct aggregate instances, or types. This is widely known as the distributed transaction trap. Symptoms: complex coordination. Teams often try to implement intricate two-phase commit protocols or rely on problematic distributed transaction coordinators. These mechanisms are notoriously difficult to implement correctly, scale reliably, and recover gracefully from failures in a highly distributed, asynchronous event-sourced architecture. Brittle system. The entire system becomes highly sensitive to partial failures. If one step within a multi-aggregate transaction unexpectedly fails, it becomes extremely challenging to roll back or appropriately compensate for changes that have already been committed by other independent aggregates. Violation of single right model. These attempts inherently contradict and break the single right model principle, where a single command strictly updates only one aggregate. This typically leads to tightly coupled, rigid systems that are inherently difficult to change or evolve. Root cause. This pitfall largely stems from a fundamental reluctance to genuinely embrace eventual consistency. Teams are accustomed to the strong acid, atomicity, consistency, isolation, durability guarantees provided by traditional relational databases that perform global transactions. When migrating to event sourcing, the powerful temptation is to forcibly apply this same rigid transaction model onto a decomposed, highly decoupled architecture. This often fails to recognize that atomicity is rigorously guaranteed only within an individual aggregate, but operations that naturally span across multiple aggregates are, by their very nature, eventually consistent. Solution: embrace eventual consistency with Saga's process managers. The correct and robust approach for coordinating operations that span multiple aggregates is to proactively accept eventual consistency and to meticulously orchestrate these long-running, multi-step business processes using Sagas or process managers. Acknowledge eventual consistency. It is crucial to understand and accept that your data will be eventually consistent across different aggregates. This means there might be a brief temporal period where one aggregate has successfully committed its change, e.g., an order has been placed, but another aggregate has not yet reacted to or processed that change, e.g., inventory hasn't yet been decremented. This transient state is perfectly acceptable if the business can tolerate it for short durations, and crucially, if you have robust mechanisms in place to reliably recover from potential partial failures. Saga's process managers. These are specialized, coordinating components thoughtfully designed to manage the entire lifecycle of a complex, long-running, multi-step business process. A Saga effectively acts as an intelligent coordinator. It attentively listens for a triggering event originating from one aggregate, e.g., the order-placed event published by the order aggregate. Based on the content and context of this triggering event, it then sends a new command to another, distinct aggregate, e.g., a reserve product command directed at the inventory aggregate. Crucially, it then waits for the corresponding response from that aggregate, which is typically in the form of another event, e.g., product reserved or product reservation failed events published by the inventory aggregate. Based on the received response, the Saga intelligently decides the precise next step in the business process. It might send yet another command to a third aggregate, confidently complete the entire process, or, critically, trigger a compensating action if a previous step unexpectedly fails. Example: order placement coordinated by a Saga. Let's revisit the order and inventory scenario to illustrate the power of Sagas. A place order command arrives, which is handled exclusively by the order aggregate. The order aggregate rigorously validates the order details and, upon successful validation, emits an order-placed event. At this point, the order aggregate's specific work for this command is complete and its internal state is consistent. A dedicated Saga instance, perhaps named Order Fulfillment Saga, listens attentively for the order-placed event. Upon successfully receiving the order-placed event, the Saga proceeds to send a reserve product command to the inventory aggregate for each item included in the order. Each inventory aggregate processes its respective reserve product command and, in turn, emits either a product reserved event, if successful, or a product reservation failed event. If, for instance, stock is insufficient, the Saga continues to listen for these product reserved and product reservation failed events, accumulating their results. If all product reserved events for the entire order are successfully received, the Saga then sends a confirm order command back to the order aggregate to finalize the order. Conversely, if any product reservation failed event is received, the Saga takes a compensating action. It sends a cancel order command back to the order aggregate and potentially notifies the customer about the cancellation. This orchestrating approach guarantees that each individual aggregate meticulously maintains its own internal consistency. And the Saga ensures that the overall complex business process eventually completes, gracefully handling intermediate failures through built-in resilience and precise recovery mechanisms. Pitfall 3. Neglecting aggregate identity and versioning. Within the crucial realm of aggregate consistency, two absolutely critical elements are frequently overlooked, or, if implemented, are done so poorly. Meticulously ensuring a strong, persistent aggregate identity and rigorously implementing robust versioning for effective optimistic concurrency control. Symptoms: lost updates, race conditions. If multiple concurrent commands attempt to modify the same aggregate instance simultaneously, and there are no proper version checks in place, one legitimate update might simply blindly overwrite another's committed changes, invariably leading to an inconsistent and corrupted state without any warning. Difficulty loading targeting. Without a clear, stable, and persistent identity for individual aggregate instances, it becomes remarkably challenging for your system to accurately load or reconstruct a specific aggregate instance's event stream from the event store in a reliable manner. Unexpected state. The aggregate's internal state might become corrupted or unexpectedly diverge from expected behavior if commands are applied based on stale, outdated information, indicating a lack of proper concurrency management. Root cause. This particular pitfall most commonly stems from a significant underestimation of the paramount importance of optimistic concurrency control within an event source system. Developers might mistakenly treat aggregate identity as merely another primary key, failing to completely grasp its fundamental role in defining and identifying a unique, specific event stream within the event store. A lax or altogether absent concurrency check during the crucial commit phase is a direct and guaranteed path to severe data integrity issues. Solution: strong identity and optimistic concurrency via versioning. Unique identity. Every single instance of an aggregate, e.g., a specific order with ID ABC123, a particular customer with ID XYZ456, must possess a truly unique identifier. This ID is absolutely crucial for two primary reasons. It definitively identifies the specific instance of the aggregate with which you wish to interact and modify. It serves as the definitive stream identifier within the event store, precisely correlating all events that exclusively belong to that specific aggregate instance. Often, a globally unique identifier, GUID-UUID, is employed for this purpose to guarantee uniqueness across distributed systems. Versioning: every time an aggregate successfully applies a command, rigorously validates it, and then confidently emits new events, its internal version number must monotonically increment. This version number accurately represents the sequential position or sequence number of the events within its specific stream. If an aggregate begins at version 0, after its first set of events is successfully committed, it transitions to version 1, then version 2 upon the next commit, and so forth. Optimistic concurrency control. This is the precise mechanism that effectively leverages versioning to actively prevent lost updates and maintain data integrity. When an application loads an aggregate from the event store for the purpose of modification, it meticulously reconstructs the aggregate's current state by replaying its historical events and simultaneously obtains its current intrinsic version. Crucially, the command requesting the modification must explicitly include this expected version. When the aggregate subsequently attempts to persist its newly generated events back to the event store performs a critical validation. It checks that the expected version provided with the command precisely matches the actual latest version of that specific event stream. If the versions do not match, it unequivocally signifies that another concurrent process has modified that exact aggregate instance in the interim. A race condition has occurred. The event store will then rigorously reject the right operation, thereby actively preventing a lost update and preserving data integrity. The client application can then typically notify the user to retry the operation, reload the aggregate state to get the latest version, or provide specific logic to handle the detected conflict. By meticulously coupling unique identity with robust optimistic concurrency control through diligent versioning, you ensure that all changes to an aggregate are atomic and consistently applied, even within a highly concurrent and potentially distributed system environment. Best practices for aggregate design. To decisively sum up effective and resilient aggregate design, consistently keep these paramount principles firmly in mind. Small is beautiful. Aggregates should be designed to be as small and compact as functionally possible, while simultaneously maintaining a single, cohesive, and clearly defined consistency boundary. This minimalist approach maximizes concurrency within the system and significantly simplifies reasoning about their behavior. One context, one aggregate, Each aggregate and its associated events should reside entirely and exclusively within a single bounded context, which represents a logical boundary for a subdomain. They absolutely should not attempt to span or cross bounded contexts directly. Root entity as entry point. All incoming commands are invariably directed only at the aggregate root. The aggregate root is deliberately designed to be the sole public interface through which the aggregate can be modified or interacted with. Internal entities within the aggregate should not be directly exposed or accessible from outside its boundary. Invariants govern boundaries. Allow your non-negotiable business rules and invariants to be the ultimate arbiters that meticulously dictate your aggregate boundaries. Always ask, what absolutely must remain consistent following a single, atomic transaction within this domain? Refer by ID, not by reference. Aggregates should exclusively refer to other aggregates solely by their unique identifiers, IDs, rather than attempting to hold direct object references or instances of other aggregates. This fundamental principle rigorously respects the inherent independence of aggregates and actively prevents accidental or implicit cross-aggregate consistency violations. Avoid bidirectional relationships. If two distinct aggregates appear to require a direct, two-way relationship, it is frequently a strong and clear signal that their defined boundaries might be incorrect, or that you are overlooking the necessity of a coordinating saga to manage their long-running interaction. Chapter summary. Aggregates are the indispensable linchpin of consistency and data integrity within an event source system. Incorrectly defining their precise boundaries, mistakenly attempting to enforce distributed transactions across them, or negligently overlooking fundamental identity and versioning principles are common yet profoundly critical design mistakes that can regrettably lead to fragile, inconsistent, and ultimately unscalable systems. By rigorously identifying your business invariants, thoroughly understanding the single right model principle, and wholeheartedly embracing eventual consistency for cross-aggregate operations, meticulously coordinating them with well-designed sagas, you can skillfully design aggregates that are inherently robust, highly performant, and resilient to unforeseen challenges. Paying close, diligent attention to aggregate identity and implementing robust optimistic concurrency control via diligent versioning are non-negotiable prerequisites for proactively preventing debilitating lost updates and rigorously maintaining impeccable data integrity within a highly concurrent environment. Mastering aggregate design represents a significant and essential step towards truly unlocking the immense power and inherently robust nature of event sourcing. Chapter 4. Projections, projections everywhere. Read model woes. The read model, your window to the events. If aggregates are the meticulous record keepers and enforcers of consistency in event sourcing's right model, then projections, also widely known as read models, are your absolutely essential window into this event-driven world. The event store, by its very nature as an append-only log, is highly optimized for efficiently writing events, but it is not inherently designed or optimized for quickly querying the current state of your system, nor for rapidly generating complex reports. This is precisely where projections step in. They vigilantly consume the continuous stream of immutable events and transform them into materialized, query-optimized views that are specifically designed for efficient read operations or for populating user interface displays. Projections are critically important for making your rich event source data easily queryable and user-friendly. However, despite their vital role, they are also a surprisingly common source of architectural complexity, widespread confusion, and significant operational issues. Beyond the much-discussed and often misunderstood eventual consistency, there are numerous practical pitfalls that can quickly transform your read models into a persistent source of frustration and inefficiency. Pitfall 1. Misunderstanding eventual consistency. The concept of eventual consistency is perhaps the most heavily discussed, and yet simultaneously one of the most frequently misunderstood aspects within the realm of CQRS, command query responsibility segregation, and event sourcing. Its implications, if not properly grasped, often lead to significant pitfalls. Symptoms: delayed, inconsistent user experience. Your business users or customers vocalize complaints such as, "I just created that order, but it's not appearing on my dashboard immediately," or "My account balance isn't updating instantly after I made that deposit." This reflects a mismatch between user expectation and system behavior. Developers forcing strong consistency. Faced with these user complaints, development teams often resort to implementing intricate workarounds or even attempting to force distributed transactions in a desperate effort to make the read model immediately consistent after every single write operation. This misguided approach frequently negates the very benefits of event sourcing and introduces immense, unnecessary complexity and fragility into the system. Lack of communication. Business stakeholders are inadequately or insufficiently informed about the practical implications of eventual consistency for the user experience. This critical communication gap inevitably leads to unmet expectations, frustration, and a breakdown in trust between the business and development teams. Root cause. This particular pitfall primarily stems from a pervasive mental model carried over from traditional monolithic, strongly consistent CRUD systems. In such architectures, a write operation typically updates the exact same database or data store from which reads are performed, inherently guaranteeing immediate consistency. In the event sourcing paradigm, the write model, managed by aggregates interacting with the event store, is deliberately decoupled from the read model, managed by projections. There is an inherent, unskippable latency as events are first persisted to the event store, then published to subscribers, subsequently consumed by various projection services, and finally written to the read model database. Underestimating this inherent latency or erroneously assuming it will always be near instantaneous is a very common and costly misstep. Solution: communicate, design for, and manage staleness. The core solution for effectively addressing this pitfall is to proactively accept, diligently manage, and clearly communicate about eventual consistency, rather than attempting to fight against its fundamental nature. Educate stakeholders. This step is absolutely paramount. Clearly and consistently explain what eventual consistency means in practical terms and articulate its specific implications for the user experience to your business users, product owners, and all relevant stakeholders. For instance, clearly communicate that an order-placed event might register instantly within the system, but it could legitimately take a few seconds for that order to visibly appear on their personal My Orders list. Bound controlled staleness. While absolute instantaneity cannot be universally guaranteed, you can purposefully design your system to keep the level of data staleness within acceptable business tolerances. Continuously monitor the lag between when an event originally occurs and when it is definitively reflected in the read model. If this lag consistently becomes too significant, it serves as a critical indicator of a performance problem within your projection pipeline, which we will cover thoroughly in the next section. User experience design, compensating actions, immediate feedback. Instead of forcing the user to endure a wait for the dynamic read model to update, whenever feasible, provide immediate, reassuring feedback directly to the user. Example: after a user successfully places an order, immediately display a "Thank you for your order" confirmation page, providing the final order details gathered directly from the command's successful processing, rather than attempting to query the potentially stale My Orders projection. Then, proactively notify the user that their order will definitively appear in their historical transaction list shortly. You can also employ strategies such as small, temporary in-memory caches on the client side, or implement optimistic UI updates, where the client immediately displays the expected state of the system, assuming the write operation will succeed, and then updates only if a confirmation of the write is received. Read your own writes pattern. For genuinely critical read-after-write user scenarios where a user must see their just committed data instantly, e.g., confirming a newly set up user profile, you can carefully employ specific patterns like passing the just committed events or the aggregate's latest committed version directly to the read endpoint. This allows the read endpoint to ensure it queries a projection that has processed at least up to that specific version, guaranteeing visibility of the latest state. directly returning the current state from the write model components immediately after a successful write operation, before an asynchronous projection has had the chance to be updated. This is a limited solution, suitable for very specific, critical cases, and should not be seen as a replacement for general-purpose projections for broader querying needs. Pitfall 2. Performance bottlenecks in projection building. Even armed with a clear understanding of eventual consistency, poorly optimized projections can nevertheless lead to unacceptable delays, rendering your read models effectively unusable or exhibiting severely degraded performance. This is a common and frustrating pitfall. Symptoms: significant lag. Your projections consistently lag considerably far behind the live event stream, resulting in data that is minutes, hours, or even lamentably days stale. This severely compromises the utility of the read model. Slow builds rebuilds. Initiating a full rebuild of a projection, e.g., after an event schema change, introducing a new projection, or during disaster recovery, takes an excessively long time. This dramatically impacts deployment cycles, prolongs maintenance windows, or causes severe operational headaches. Resource exhaustion. Your projection services exhibit unusually high consumption of CPU, memory, or database I/O resources, unequivocally indicating inefficient processing logic or an overloaded infrastructure. Root cause: inefficient event processing logic. Individual projection handlers might contain overly complex queries against an already denormalized projection database, perform unnecessary data joins, or execute heavy computational tasks for every single event they process. This synchronous, per-event heavy lifting accumulates rapidly. Lack of proper indexing. The underlying read model database, where your projections materialize, is not adequately indexed for the specific read queries that are being performed against it. This leads to inefficient full table scans or suboptimal query execution plans. Unoptimized database writes. Each incoming event triggers a separate, fine-grained write or update operation to the read model database. This misses critical opportunities for batching multiple database writes together, which is generally orders of magnitude more efficient by reducing I/O overhead and transaction commits. Rereading excessive data. Event handlers might unnecessarily reread large amounts of data from the projection store for each incoming event, instead of efficiently updating incrementally or leveraging local caching mechanisms. Ineffective use of snapshots. For very long-lived aggregates or high-volume event streams, reconstructing the read model from scratch involves replaying the entire historical event stream from the very beginning. If not properly managed with snapshots, this can be an extremely computationally intensive and time-consuming process. Solution: optimize event processing, batch writes, and utilize snapshots indexes. Optimizing projection performance is absolutely critical for ensuring both the usability and operational efficiency of your event source system. Lean event handlers. The logic within your individual projection handlers for each event should be designed to be as simple, direct, and efficient as possible. The primary goal is to update the read model based on the event's payload with minimal overhead. Strictly avoid complex joins, unnecessary lookups, or heavy real-time computation within the event handlers themselves. Batching writes. Instead of performing a distinct database write operation for every single processed event, rigorously consider batching your updates. Accumulate a set of events, e.g., processing 100 or 1,000 events in a queue, and then perform a single bulk insert, update, or upsert operation to the read model database. This strategy significantly reduces repetitive I/O overhead and minimizes transaction commit overhead. Indexing and denormalization. Ensure that your read model database is strategically and comprehensively indexed for the exact queries it needs to serve. Projections should be heavily denormalized, meaning all data required for a specific query is stored in a single, flat structure, even if it entails duplicating data. This minimizes complex data joins at query time, leading to faster reads. Snapshots for read model rebuilds. For aggregates that generate an exceptionally large number of events over their lifetime, taking periodic snapshots of their internal state within the event store. These are distinct from read model snapshots initially, but help for aggregate reconstruction, can dramatically speed up aggregate state reconstruction for the right model. More directly for read models, you can store periodic snapshots of the read model's materialized state. When rebuilding a read model, you can then commence processing from the latest read model snapshot and apply only the events that have occurred since that snapshot point, rather than replaying the entire event history from the beginning of time. Projection partitioning/parallelization. Distribute and parallelize the work of processing events across multiple projection instances or threads. For example, events belonging to specific aggregate IDs can be consistently routed to dedicated projection instances, e.g., by using a hash of the aggregate ID. This allows for concurrent processing and effectively scales out your projection services horizontally. Pitfall 3. Duplication of projection logic/inconsistent read models. As your event-sourced system inevitably grows and evolves, you might find yourself needing several different projections that, at a high level, cover similar or overlapping data domains. This frequently leads to a deeply problematic scenario where essential projection logic is either inadvertently duplicated or subtly diverges, causing major headaches. Symptoms: inconsistent data presentation. Different parts of your application, or various user roles, might regrettably observe subtly inconsistent data for what should fundamentally be the exact same underlying business entity. For example, one dashboard might depict an order as processing, while another simultaneously shows it as confirmed due to slightly different logic applied in their respective projection builds. Maintenance nightmare. A fundamental and critical change to an event's definition, e.g., adding a new crucial field to the order-placed event payload, necessitates updating the event handler logic across multiple, disparate projection services. This process is inherently error-prone, time-consuming, and significantly increases the risk of introducing new bugs due to missed updates. Ad hoc projections. Individual teams or even single developers might autonomously spin up new projections from scratch without properly leveraging existing logic, or without adequately considering the broader consistency implications across the entire system. Root cause. This particular pitfall frequently arises from a lack of centralized coordination, insufficient architectural discipline, or poor code organization specifically around projections. Different teams might independently build their own unique projections without a shared understanding of common event processing rules, or without ready access to reusable, standardized components. The powerful temptation to quickly spin up a new query model often bypasses any rigorous consideration for long-term maintainability, consistency, and reusability. Solution: centralized event handling or shared read model factories. To effectively combat the issues of logic duplication and data inconsistency across your read models, aim for strategic reuse and establish clear ownership. Shared projection libraries modules. Identify common event-to-read model transformation logic and rigorously encapsulate it within reusable libraries, modules, or distinct frameworks. For example, if multiple projections consistently need to calculate a running total from a stream of item-added and item-removed events, create a shared function, class, or service that precisely performs this specific calculation, ensuring consistency. Clear ownership and documentation. Assign unambiguous and clear ownership to specific read models and their underlying projection logic. Maintain thorough and up-to-date documentation that precisely articulates how each event contributes to and influences different read models across the system. This clarity reduces guesswork and prevents accidental divergences. Review and harmonize. Periodically review your existing projection logic across different services to actively identify instances of logical duplication and discover opportunities for refactoring into logical sharing. Proactively work to harmonize and standardize different ways of processing the same event, ensuring a consistent approach system-wide. Views over denormalized data. Sometimes, rather than creating entirely separate read model databases or tables for slightly different querying needs, it is more efficient to build a single, highly denormalized, master projection table. Then, construct specific relational database views or equivalent querying layers in NoSQL databases, on top of this single master projection. This allows different query patterns to use the same underlying materialized data, minimizing duplication and increasing consistency. Pitfall 4. Read model schema evolution and rebuilding challenges. Just like your core event schema in the event store, the schema of your read models will inevitably need to evolve as your business requirements change and your understanding of the domain deepens. However, gracefully evolving a materialized view, a projection, can present particularly significant challenges, differing markedly from traditional database schema migrations. Symptoms: downtime degradation during rebuilds. Modifying the schema of an existing read model frequently necessitates a full rebuild of the projection by replaying the entire event stream. This can lead to significant downtime for the read service or severely degraded performance during the often lengthy rebuild process, impacting end users. Complexity in supporting multiple versions. If your system needs to simultaneously support older versions of your application while a new projection is being built for a newer application version, managing multiple parallel versions of your read models and the corresponding projection code that builds them adds considerable complexity and operational overhead. Data migration headaches. When the time comes to deprecate older read models, migrating existing users or converting historical data from one projection schema to an entirely new one can be an exceptionally complex, time-consuming, and inherently risky endeavor. Root cause: this pitfall most often stems from an underestimation of the inherent impact that schema changes have on materialized views. While events themselves are immutable, read models are highly mutable and entirely derived from those events. A lack of a clear, well-defined, and robust strategy for gracefully evolving these derived views can lead directly to significant operational challenges and project delays. Solution: blue-green deployment for projections and versioning read models. The most robust and generally recommended way to handle read model schema evolution is through deployment strategies that actively minimize downtime and carefully manage transitions. Blue-green deployment for projections. This is frequently the most reliable and least impactful strategy for schema evolution in read models. The blue environment represents your current, active, live projection, serving current application traffic. When you need to implement a schema change, deploy the new version of your projection code to a separate green environment. This green instance begins subscribing to the event stream or a copy of it, and systematically building its updated read model from scratch or from a carefully selected recent snapshot into a new, separate database or distinct table with the updated schema. Once the green projection is fully caught up with the event stream, has entirely rebuilt its view, and passes all integrity checks, you then switch your application traffic, e.g., by updating a connection string, a load balancer rule, or a DNS entry to transparently read from the newly built green projection. After the successful switch, the blue projection can be retained online for a defined rollback period, providing a safety net before it is eventually decommissioned. This strategy effectively allows for zero downtime schema evolution. Version projections. If your system truly necessitates supporting multiple application versions, e.g., App 1 and App 2, simultaneously for an extended period, you might need to run explicitly version projections in parallel, e.g., separate databases or tables like order sumarif 1db, order sumarif 2db. This strategy undeniably adds operational overhead in terms of resources and management complexity, but it provides the necessary flexibility for backward compatibility during extended transition periods. Incremental migrations evolution. For exceptionally large read models where even a blue-green rebuild might be deemed too slow due to data volume, explore more advanced strategies for incremental updates or data transformations. This might involve applying schema changes directly to the existing read model, and then writing sophisticated compensating logic to transform dirty or outdated data, or utilizing specialized online schema migration tools if your chosen database supports them. However, for materialized views rigorously derived from an immutable event stream, a complete rebuild executed via blue-green deployment is often the simplest, cleanest, and safest path to ensuring data integrity. Best practices for read models. To ensure your sophisticated projections consistently remain a valuable asset to your system, rather than becoming a frustrating liability. Consistently adhere to these essential best practices. Optimize for reads. Projections exist with the singular purpose of serving queries with maximum efficiency. Therefore, prioritize aggressive data denormalization, create highly custom tables tailored to specific query needs, and strategically apply appropriate indexing for your precise query patterns. Resist the common urge to build a generic, one-size-fits-all read model. True efficiency comes from specialization. Idempotency is non-negotiable. Individual projection handlers must be designed to be fully idempotent. This means that processing a given event multiple times should consistently produce the exact same resultant state in the read model as processing it only once. This principle is absolutely crucial for building resilient systems in distributed environments where events can be delivered multiple times due to at least once delivery guarantees. Monitor lag actively. Implement continuous and active monitoring of the lag or delay between the timestamp of the latest event written to the event store and the timestamp of the last event successfully processed by your projections. A consistently high or increasing lag is a critical indicator of underlying performance problems within your projection pipeline that demand immediate attention. Clear separation of concerns. Maintain a rigorous and unambiguous separation between your projection, building logic, and your aggregates right model. Under no circumstances should you mix read-side and write-side concerns within the same component, as this significantly complicates reasoning and introduces tight coupling. Test thoroughly, especially with history. Test the integrity and accuracy of your projections rigorously. When creating entirely new projections or making significant changes to existing ones, systematically validate them against a substantial dataset of historical event data to ensure they correctly reconstruct the expected state under various scenarios. Use automated regression tests against historical event streams. Avoid read-side commands. Read models should be purely passive and solely dedicated to serving queries. Explicitly design them not to trigger commands, initiate side effects, or directly modify the state of other parts of your system. They are strictly passive consumers of the event stream. Chapter summary. While aggregates meticulously handle the right side of your system, projections strategically unlock the formidable query power of your event source data, providing a specialized, optimized window into your system's current and historical states. However, the path to implementing truly effective and reliable read models is undeniably fraught with significant challenges. Misunderstanding and subsequently mismanaging eventual consistency, battling persistent performance bottlenecks during the crucial projection building phase, wrestling with duplicated or subtly inconsistent logic, and painstakingly navigating complex read model schema evolution are all pervasive yet critical pitfalls that can severely hinder your progress. By proactively educating stakeholders about consistency trade-offs, diligently optimizing your projection pipelines, actively avoiding logic duplication through strategic use of shared components and clear ownership, and employing robust deployment strategies like blue-green for schema changes, you can definitively ensure that your projections evolve into valuable assets rather than becoming persistent operational liabilities. Furthermore, rigorous testing, particularly against comprehensive historical event data, will unequivocally ensure their consistent accuracy, reliability, and ultimately their long-term value to your application. Mastering projections is an absolutely essential step towards realizing the full, transformative benefits of event sourcing, making your rich event data widely accessible, performant, and truly usable throughout your entire application ecosystem. Chapter 5, Evolving Events, the Schema Versioning Nightmare, the Immutable Dilemma. At the core of event sourcing, as we detailed in Chapter 1, lies the principle of event immutability. Once an event, a declaration of something that has happened, is recorded in the event store, it cannot and must not be changed. This is the cornerstone of auditability, temporal querying, and the reliable historical record that makes event sourcing so powerful. However, the world, and indeed your business, is anything but immutable. Business requirements evolve, your understanding of the domain deepens, and technological capabilities change. New features require new data, and sometimes, old data fields become obsolete or need to be restructured. This presents a fundamental conundrum. How do you gracefully, reliably, and efficiently adapt the structure of your events when the existing ones, once recorded, are permanent? This challenge is precisely what gives rise to the dreaded schema versioning nightmare in event sourcing. Ignoring or mishandling event schema evolution is a direct path to a brittle, unmaintainable, and ultimately failing system. Pitfall 1. Ignoring event schema evolution, the head-in-sand approach. The easiest and most perilous pitfall is to simply ignore the problem of event schema evolution, hoping it will somehow resolve itself or never become a significant issue. This is the head-in-sand approach. Symptoms: system crashes or misbehavior. When you deploy new versions of services and attempt to replay old events, e.g., during aggregate reconstruction, projection rebuilds, or a new feature's historical analysis, your system unexpectedly crashes or behaves incorrectly. This is often due to deserialization failures, missing fields, or unexpected data types. Data inconsistency. New events are generated with data structures that older, still-running services fundamentally cannot understand or properly process. This leads to silent data loss or incorrect behavior in downstream consumers that haven't been updated yet. Implicit, unstable logic. To cope with the inevitable schema differences, developers resort to ad hoc, unstable, and often verbose conditional logic spread throughout the codebase. You'll see numerous if field equals null or try-catch blocks and many version-specific switch statements, turning your domain logic into a tangled mess of compatibility layers. Root cause. This pitfall stems from several misunderstandings or underestimations. Underestimation of long-term evolution. Developers often focus on the immediate implementation, neglecting the inevitability that systems will evolve over years, not just months. Assumption of constant structure. There's an implicit, often unspoken, assumption that an event structure, once defined, will remain constant throughout the system's lifetime. Lack of strategy and tooling. Teams fail to establish a clear, formalized strategy or adopt appropriate tooling for managing event schema changes from the outset. Solution: acknowledge and plan for evolution from day one. The most crucial step is to acknowledge that event schema evolution is not an if, but a when. It's a fundamental part of working with immutable data and distributed systems. Events are long-term contracts. Treat your events not just as messages, but as part of your system's long-term storage contract. Once an event is persisted, it's there forever. This mindset shift forces you to think about forward and backward compatibility. Implement a formal versioning strategy. Decide on a clear, consistent approach for versioning your events. This could be implicit, e.g., order placed v1, order placed v2, etc., as distinct types, or explicit, e.g., adding a version field within the event's metadata or payload. The chosen strategy should be consistently applied across all events. Consider event schema registries and validation. For larger, more complex systems or those with many independent services producing and consuming events, investing in a formal event schema registry, like Confluent Schema Registry for Kafka-based systems, can be invaluable. These tools provide centralized management of event schemas, enforce compatibility rules, and allow for automated validation of events as they are produced and consumed. Pitfall 2. Breaking changes to existing events, the Big Bang migration. Despite the immutable nature of events, a common temptation is to treat event schemas like traditional database table schemas that can be altered in place. This leads to the perilous Big Bang migration scenario. Symptoms: deletion or renaming of fields. Developers attempt to clean up event schemas by removing old fields that are no longer used or by renaming existing fields. This immediately breaks any historical events that contain those old structures. Fundamental data type changes. Changing a data type from, say, a string to a complex object, or modifying the meaning of an enumeration value, fundamentally alters the contract of historical events. Painful full migrations. The only way to rectify these breaking changes is to perform a full, highly complex, and often risky migration of the entire accumulated event stream. This typically involves replaying all historical events from the original event store, transforming each event on the fly to the new schema, and then persisting them into a new event store or a new version stream. This process is often downtime-heavy, resource-intensive, and prone to errors. Root cause: treating events like mutable database schemas, a direct carryover of the CRUD mindset where developers are accustomed to alter table commands. Lack of understanding of immutability's implications, not fully grasping that immutable means really immutable even in the face of evolving requirements. Desire for clean schema, a understandable yet ultimately misguided desire to eliminate legacy, fields, or historical baggage from the current event definition. Solution: never mutate old events. Always add, never remove. The golden rule for event schema evolution is simple. Events are additive. You can always add new fields, but you should never delete, rename, or change the fundamental data type or meaning of existing fields within a specific event version. Rule of thumb: additive evolution. Adding fields. This is the safest way to evolve an event. New versions of your event producer can start including the new field. Older consumers will simply ignore the new field. Newer consumers checking for an older version of the event will know the field might be missing and can use a default value or handle its absence. Deprecating fields. If a field is no longer needed, mark it as deprecated in your code and documentation. New events should stop sending data for it, but existing events in the stream will still contain it. Consumers must continue to tolerate its presence. Renaming fields. Instead of renaming, add the new field with the desired name and treat the old field as deprecated. Over time, consumers can migrate to using the new field. Changing data type semantics. If a field's type or meaning changes fundamentally, it's often best to introduce a new version of the entire event or introduce a new event type altogether if the meaning has drastically shifted. Versioning within events. Explicitly mark your events with version numbers. This can be done by creating separate event types, e.g., order placed v1, order placed v2, or by including a version field directly within the event's metadata or payload. This version number tells consumers exactly what structure to expect. Forward compatibility, tolerant reader robustness principle. Design your event consumers, including aggregates and projections, to be tolerant readers. This principle dictates: be conservative in what you do, be liberal in what you accept from others. Your code should be robust enough to handle unknown fields. If an event contains a field the consumer doesn't recognize, it should simply ignore it, not crash. Missing optional fields. If a field is present in a newer version but missing in an older version, the consumer should handle its absence gracefully, e.g., by using a default value. Case study example. Adding a shipping method to order placed. Original event, v1, order placed contains orderid, customerid, order date. Evolution, v2, a new requirement emerges to track the shipping method. You don't change the v1 event. Instead, you introduce order placed v2, which now contains orderid, customerid, order date, and shipping method. Consumers. An old service expecting order placed v1 will only process the orderid, customerid, order date fields even if it receives an order placed v2, ignoring shipping method. A new service can explicitly handle both order placed v1, expecting shipping method to be absent and applying a default, and order placed v2, using the provided shipping method. Pitfall 3. In place event transformation during replay, the on-the-fly trap. While the never mutate old events rule simplifies production, it introduces complexity when reading events. A common pitfall here is trying to perform all historical event transformations on the fly as they are replayed for aggregate reconstruction or projection building. Symptoms: monolithic deserialization logic. Your code contains a single, massive piece of deserialization logic that attempts to transform all historical event versions into the very latest format before they are processed by the aggregate or projection. This results in deeply nested if-else statements or switch cases for every single past version. Complex tangle of conditional logic. The core domain logic within your aggregates or projections becomes polluted with conditional checks, if event version equals v1, making it extremely difficult to read, understand, and maintain. Performance degradation. As the system ages and the number of event versions grows, the on-the-fly transformation for every event during replay can significantly degrade performance during aggregate loading or projection rebuilds. Root cause: desire for clean aggregate logic. Developers want their aggregate's business logic to only ever deal with the latest, most convenient event structure, pushing all version compatibility concerns into a hidden corner of messy deserialization. Underestimation of maintenance burden. The initial simplicity of a single transformation function is deceptive. Its complexity grows linearly with the number of versions. Misunderstanding of event upcasting. Not being aware of a more structured and manageable pattern for handling historical event versions. Solution: explicit event upcasting linear transformation chain. The professional and maintainable way to handle historical event versions is through explicit event upcasting. Principle: linear transformation chain. Events are transformed in a linear, version-by-version chain, almost like a series of small, dedicated functions. An event of version 1 is transformed to version 1.1, then version 1.1 to version 1.2, and so on until it reaches the desired latest version. Dedicated upcaster functions. Each individual upcaster function is responsible for knowing how to transform only one specific version of an event to its next immediately newer version. For example, an order-placed v1 upcaster might take order-placed v1 and convert it to order-placed v2. Benefits: simplicity of individual upcasters. Each upcaster is small, focused, and easy to test. Gradual evolution. You can introduce new versions and their upcasters incrementally without affecting existing upcasters. Clear responsibility. The transformation logic is clearly separated and encapsulated, keeping the core domain logic clean. Auditability. You can clearly see the chain of transformations applied. Separation of concerns. This upcasting logic resides outside the aggregate's core business logic. When an event is loaded from the event store, it first passes through the upcasting pipeline. By the time it reaches the aggregate's apply method, the function that updates the aggregate's state based on an event, it is already in the latest expected format. Example: let's say order placed v1 has no shipping method, but order placed v2 requires one. When order placed v1 is loaded, an order placed v1 to v2 upcaster would fire. This upcaster would take order placed v1 and return a new order placed v2 with a default shipping method added. The aggregate's apply method then only deals with order placed v2, simplifying its internal logic. This approach creates a clear historical migration path for your event data without ever mutating the original, immutable events. Pitfall 4. Neglecting to propagate version changes to projections. While managing event evolution for aggregate reconstruction is crucial, it's just one side of the coin. A commonly overlooked pitfall is neglecting how these version changes impact your read models, projections. Symptoms: inconsistent read models. After new event schema versions are introduced, your read models may fail to update correctly, or worse, become subtly inconsistent due to their inability to correctly process the new or old event structures. Failed projection rebuilds. If you attempt to rebuild a projection from scratch using the full historical event stream, the rebuild process might fail outright or produce incorrect data because the projection's processing logic isn't properly wired up to handle all historical event versions. Manual intervention. Teams resort to manual data fixes or complex one-off scripts to correct projection data after an event schema change, indicating a lack of a robust strategy. Root cause. Focus on right model first, and only. Development teams often place primary emphasis on ensuring the right model aggregates can correctly handle event evolution, mistakenly assuming that projections will somehow magically adapt or that their problems are entirely separate. Assumption of projection self-healing. There's an incorrect assumption that projections, being derived, are inherently self-healing regarding event schema changes. Lack of coordinated strategy. Events and projections are often treated as independent concerns, leading to a lack of a cohesive, synchronized strategy for their evolution. Solution: coordinated evolution of events and projections. Effective event schema evolution requires a coordinated approach that encompasses both the right model and all derived read models. Projections must be version-aware. Just like aggregates, your projection services and their event handlers need to be capable of intelligently processing all past versions of the events they consume. This means the projection code must contain logic to correctly interpret data from order placed v1, order placed v2, and any subsequent versions. Upcasting for projections. Projections can and often should leverage the same explicit event upcasting mechanisms used by aggregates. Before an event is passed to a projection's specific handler logic, it can first pass through the upcasting pipeline to be converted into the latest version. This keeps the projection logic clean and focused only on the current event structure. Alternatively, a projection can have version-specific handlers if the transformation is simple, or if a field is simply added, the projection logic can handle optionality, e.g., event get shipping method, or else standard. Blue-green deployments revisited. This strategy, highlighted in Chapter 4 for general read model evolution, is especially vital when event schema changes necessitate a full or partial rebuild of projections. When a new event version is introduced that affects a projection, you can deploy a green version of the projection service that understands the new event versions and includes any updated projection logic. This green service builds a new read model or updates an existing one on a separate table schema by replaying the entire event stream, applying upcasters as necessary to handle all historical versions. Once fully caught up and consistent, application traffic is switched to the new green read model. This ensures a seamless transition for users. Best practices for event schema evolution. To recap and solidify your approach to navigating the schema versioning nightmare, embrace these best practices. Think additively. This is the bedrock principle. Always introduce new fields, new event types, or new versions of events by adding to existing structures. Never rename, remove, or fundamentally alter the type or meaning of fields in events that have already been persisted. Use explicit versioning where necessary. Either adopt distinct event types, e.g., order placed v1, order placed v2, or embed a clear version number within your event's metadata. This provides unambiguous signals to consumers about the event structure. Adopt the tolerant reader principle. Design your event consumers, aggregates, projections, external systems, to be resilient to unexpected fields and gracefully handle missing optional fields. This cushions the impact of additive schema changes. Implement automated upcasting. Develop a clear, structured, and automated mechanism for event upcasting, transforming older versions of events into newer ones. This keeps your domain logic clean and makes evolution manageable. Consider a schema registry. For complex, distributed systems with many services and events, a centralized schema registry can automate schema verification, enforce compatibility rules, and provide a single source of truth for all event definitions. Rigorously test event evolution. Do not assume your system will handle event evolution gracefully. Create dedicated tests that replay historical events, including various versions, through your updated aggregates and projections to simulate real-world evolution scenarios. This identifies issues early, before they become production nightmares. Chapter summary. Event immutability is a core strength of event sourcing, offering unparalleled auditability and temporal capabilities. However, this power comes with a significant challenge: gracefully managing the evolution of your event schemas over time. Ignoring this challenge by burying your head in the sand will lead to system fragility and data inconsistencies. Attempting big bang migrations by breaking past event contracts is a recipe for disaster. The key to success lies in proactive planning, embracing additive changes to your event structures, and implementing explicit event upcasting mechanisms. Furthermore, it's crucial to coordinate the evolution of your events with the evolution of your read model's projections, ensuring they remain consistent and performant. By treating event schemas as long-term contracts and adopting disciplined practices, you can transform the schema versioning nightmare into a manageable, albeit complex, ongoing process of system adaptation and growth. Chapter 6, Debugging and Testing, Navigating the Temporal Labyrinth. The challenges of a temporal system. Event sourcing, by its very nature, introduces a profound temporal dimension to your system's data and behavior. Instead of merely reflecting a single, current state, your system meticulously records every state transition as it occurred over time. While this chronological ledger offers immense power for auditability and reconstruction, it fundamentally shifts how you approach debugging and testing. Your familiar tools and ingrained habits from traditional, state-based systems might not only prove insufficient, but can actively mislead you in this new environment. This chapter will delve into why traditional approaches fall short and how to adopt new strategies for navigating the temporal labyrinth of event-sourced systems. Pitfall 1. Relying on traditional debugging, static state inspection. A common, yet misleading, pitfall is to rely solely on traditional debugging techniques that focus on inspecting the static, current state of your databases or objects. Symptoms: elusive bugs. You find it incredibly difficult to pinpoint the root causes of reported bugs by simply examining the read models, your query databases, or the final state of an aggregate. The system says the customer balance is $500, but why is it $500 instead of $550? The answer isn't obvious from inspecting the number alone. Transient or hard-to-reproduce issues. Bugs appear intermittently or are only reproducible under very specific, hard-to-replicate circumstances. A bug might occur only after a particular sequence of operations that is not obvious from the final outcome. What without why or how? Your current database state tells you what the system looks like now, but gives little insight into how it got there or why a particular value is present. Root cause. This pitfall arises because sequence matters. A bug in an event-sourced system often isn't about a wrong value in a field, but about a flaw in how events are applied or how a sequence of legitimate operations interacts. The final state might be correct, but an intermediate state was wrong, or the transition logic from one state to the next was faulty. Asynchronous updates. Problems might reside in the asynchronous projection logic, covered in Chapter 4, where the read model is updated incorrectly, even if the write model, the event stream, is perfectly sound. Debugging the read model directly won't reveal the source of the problem in the event stream or projection handler. History is hidden. In a traditional system, you might rewind a debugger or look at transaction logs. In event sourcing, the explicit history is your primary source of truth, yet if you're not looking at it, you're debugging blind. Solution: embrace temporal debugging and event trail analysis. The key to effective debugging and event sourcing is to shift your focus from inspecting static state to understanding the dynamic flow of events. Event stream as core evidence. Always treat the immutable event stream as the primary source of truth for understanding system, behavior, and diagnosing issues. Every change, every decision, every relevant fact is there, time-stamped and ordered. Tools for navigating history. Invest in or build tools that allow you to easily query, filter, and navigate your event store. Modern event stores often come with UIs that let you inspect event payloads, filter by event type or aggregate ID, and even replay subsets of events. Specialized debuggers or frameworks might allow you to replay an aggregate-specific history step-by-step to see its state evolve through each event. Deterministic reproducibility. One of the greatest advantages of event sourcing is deterministic reproducibility. If you encounter a bug, you can capture the exact sequence of events that led to it. By replaying this precise sequence through your application code, in a debugger or a dedicated test environment, you can reliably reproduce the bug every single time, making it much easier to isolate and fix. Mini case study. Imagine a loyalty point system where a customer complains their points balance is incorrect. Traditional debugging might only show a final balance of 450 points in the customer points table. However, inspecting the event stream for that customer reveals events like points added, 100, points redeemed, 50, points added, 500, points expired, 100. If your points expired logic was faulty, and, for example, incorrectly applied twice, the event stream provides the precise sequence to reproduce the error and identify the bug in the event handler for points expired. Without the event stream, you're guessing. Pitfall 2, insufficient testing of state transitions, missing the behavior. Accompanying the debugging challenge is a related pitfall in testing, focusing solely on the final state of an entity rather than the dynamic behavior that produces that state. Symptoms: passive tests. Your test suite mostly consists of asserting against a final database state after an operation. Tests might pass, but subtle business logic errors or edge cases in how customer transitions from new to active to premium might slip through because the intermediate behavior isn't explicitly verified. Invariance broken invisibly. An aggregate's invariance might be violated during an intermediate step of a complex operation, but then seemingly fixed by a subsequent part of the operation, masking the underlying issue. Works on my machine syndrome. A test passes reliably in a local developer environment, but becomes flaky or fails intermittently in a continuous integration (CI) pipeline, especially when concurrency comes into play. Root cause: familiarity bias. Developers are often more comfortable with traditional unit and integration testing, where the focus is on a static database state after an operation completes. Modeling difficulty. It can feel less intuitive to model tests around sequences of commands and the events they produce, rather than simply asserting the final form of a database record. Ignoring invariance. Not considering the precise business rules that must be maintained during each state transition, not just at the end. Solution: event-driven testing, behavioral-driven development principles. The event sourcing paradigm aligns beautifully with behavioral testing and principles like given when, then. This approach focuses on explicitly testing the state transitions and emitted events, not just the final state. Right model testing, aggregates. These tests should primarily verify the aggregate's decision-making logic and its invariant enforcement. Given an initial state of the aggregate, represented by a predetermined series of past events that define its history, e.g., order created, item added, A, item added B. When a specific command is issued to the aggregate, e.g., remove item A. Then, a precise set of new events are expected to be emitted by the aggregate, e.g., item removed, A, or, if the command is invalid given the given state and rules, an expected error should occur. This structure forces you to think about behavior. What happened, given, what action was taken when, and what was the result then. Read model testing, projections. These tests verify that your projections accurately transform event streams into the desired read model state. They focus purely on the event-to-read model mapping. Given a specific stream of events, e.g., customer registered, customer address updated, when these events are processed by the projections event handlers, then the read model state, e.g., the customer dashboard table, contains the expected data and structure. This ensures your read models accurately reflect the right model over time. Process manager saga testing. Sagas coordinate multiple aggregates over time. Their tests should verify this coordination logic. Given a saga instance is in a certain state, perhaps having just processed a payment received event. When a new event is received by the saga, e.g., product shipped, then the saga should issue a specific command, e.g., close order, to another aggregate or transition to a new internal state or complete its process. Test fixtures. To facilitate these tests, create helper utilities or test fixtures that allow you to easily construct an aggregate state by replaying a list of events. Capture events emitted by an aggregate when a command is applied. Assert the contents and types of emitted events. Pitfall 3, ignoring asynchronous nature of projections, timing bugs. A common source of frustration is when tests involving projections behave inconsistently. They pass locally but intermittently fail in CI production or exhibit discrepancies between the write model and read model results. Symptoms: flaky integration tests. Tests involving command through to read model queries pass sometimes, but fail another time without code changes. Read after write issues. Test assertions are made on the read model immediately after a command is processed, but the data isn't yet reflected in the projection. Race conditions. Tests accidentally introduce or expose race conditions due to a lack of awareness of the asynchronous nature of event processing. Root cause, assumption of immediate consistency. Developers incorrectly assume that once an event is written to the event store, the read models are instantly updated. This is rarely true in a fully decoupled event source system due to network latency, message queue processing, and database writing time. Lack of asynchronous awareness in test design. Tests are not designed to account for the time lag inherent in this asynchronous data flow. Uncontrolled latency. In local environments, latency might be minimal, making tests pass. In a CI server or production, real-world network and processing delays expose timing issues. Solution: await consistency, contract testing, and deliberate integration. Effective testing for projections requires acknowledging and managing their asynchronous nature. Await consistency in tests. For integration tests that span from command to read model, introduce explicit mechanisms to wait for the projection to catch up. This might involve polling. Repeatedly query the read model database until the expected data appears. Set a reasonable timeout to prevent infinite loops. Synchronization points. If your message queues or projection frameworks offer them, use explicit acknowledgments or barriers to ensure event processing has reached a certain point before asserting. Event count assertions. Confirm that a projection has processed a specific number of events before querying its state. Contract testing. Separate tests should be written for the event producers, aggregates, verifying the shape and meaning of events they emit, and event consumers, projections, verifying they can correctly interpret and process events of defined contracts. This ensures a clear contract between producers and consumers. If an event definition changes, only the relevant contract tests fail, making it clear which components are affected. Deliberate integration tests. While unit and behavioral tests for aggregates and projections are fast and focused, slower, broader integration tests confirm the entire chain works. These slice tests might involve sending a command, verifying the event store, then waiting for and asserting the read model state. For critical flows, dedicated end-to-end or system tests running against a near-production environment can provide the final confidence. Pitfall 4. Lack of comprehensive regression testing with historical data. A subtle but potentially devastating pitfall is failing to comprehensively regression test your system with its own historical data. Symptoms: resurfacing old bugs. Deploying new features or bug fixes unexpectedly causes old bugs to reappear, especially when processing historical data or during a projection rebuild. Failed projection rebuilds. A seemingly minor change to event definitions or projection logic breaks the ability to rebuild a projection from scratch using the full historical event stream, leading to data inconsistencies or outright rebuild failures. Unstable event upcasers. Changes to event schema, covered in Chapter 5, are deployed without sufficient testing against accumulated historical data, leading to upcasting logic failing or producing incorrect results for old events. Root cause: short-sighted testing. Tests are written only for current system behavior or newly introduced features, neglecting the backward compatibility that is critical for event sourcing. Fear of tedious replay. The perceived effort of manually replaying large volumes of historical data for testing leads teams to skip this crucial step. Underutilization of event store. Not fully grasping that the immutable historical event stream is not just for auditing or replay, but a powerful, deterministic asset for thorough regression testing. Solution: historical data, replay for regression testing. The immutable nature of the event store provides an incredible asset for regression testing. The ability to deterministically replay any sequence of historical events. Capture production events anonymized. Periodically or ideally, continuously in a secure, non-production environment, capture realistic, anonymized production event data. This provides a golden source of real-world scenarios, including edge cases and volumes you might not foresee in synthetic test data. Automated replay harness. Build robust automated test harnesses and scripts that can programmatically replay these captured historical event streams against new versions of your aggregates, projections, and any other event consumers. Comparison and validation. After replaying historical events, compare the resulting state of your aggregates, reconstructed from the replayed events, and your derived read models against known good historical states or established assertions, golden masters. This is particularly potent for verifying the correctness of your event upcasers, Chapter 5, and ensuring that projection evolution handles all past event versions as expected. Tools can be developed to compare generated aggregate state and read models against pre-recorded expected outcomes. Simulate real-world scenarios. Use these historical replays to rigorously test performance under realistic load conditions. You can also simulate various recovery scenarios, such as rebuilding all read models from scratch, and verify that your system recovers correctly and reproducibly. This validates your operational playbooks and architectural resilience. Best practices for debugging and testing. Mastering debugging and testing in an event source system requires a shift in mindset and a commitment to specific practices. Event store as the foremost source of truth. When debugging, always start by inspecting the raw event stream for the problematic aggregate. It tells the definitive story of what happened. Behavior over state in tests. Prioritize testing the behavior of your system, commands producing events, events changing aggregate state, sagas orchestrating processes, rather than just the final, static state of your read models. Automate event replay. Build internal tooling or leverage existing frameworks that facilitate the easy replay of specific event streams. This is invaluable for rapid bug reproduction and localized debugging. Robust observability. Instrument your event handlers, aggregates, projections, and sagas with comprehensive logging, tracing, and metrics. Track event flow, processing times, and any errors. Good observability acts as an early warning system and provides crucial context for debugging. Small, focused tests. Break down complex scenarios into smaller, manageable, and highly focused test units. Test aggregates in isolation, test projections in isolation using mock event streams, and test sagas as state machines reacting to events. Mock external systems. For deterministic and reliable testing, isolate your event-sourced core by mocking any interactions with external systems, e.g., payment gateways, external APIs. This ensures your tests are repeatable and not dependent on external service availability or fluctuating performance. Chapter Summary. Event sourcing's unique temporal nature, while powerful, introduces distinct challenges for debugging and testing. Your familiar state-centric approaches will fall short where the sequence of events, asynchronous updates, and long-term historical compatibility are paramount. Ignoring these challenges leads to elusive bugs, flaky tests, and ultimately, an unreliable system. The key to success lies in embracing the temporal dimension. Shift your debugging focus to analyzing the immutable event stream. Design your tests to verify behavior and state transitions using techniques like given when, then. Explicitly account for the asynchronous nature of projections in your integration tests by awaiting consistency. Crucially, leverage the event store as a powerful asset for comprehensive regression testing, replaying historical data to validate forward and backward compatibility. By adopting these new mindsets and tools, you can confidently navigate the temporal labyrinth, transforming the inherent complexity of event sourcing into a source of deterministic control and robust system reliability. Chapter 7, Operational Overdrive, Deployment, Monitoring, and Recovery. The Production Reality Check. Through the previous chapters, we've explored the conceptual elegance of event sourcing, the art of defining meaningful events, designing coherent aggregates, and managing the complexities of read models and schema evolution. These are crucial aspects of development and architectural design. However, the true test of any system, especially one built with advanced patterns like event sourcing, comes in production. This is where development meets operations, and the seamless theoretical flow of events faces the harsh realities of networks, hardware failures, resource contention, and user expectations. Event sourcing introduces a unique set of operational challenges that can easily be underestimated. The raw simplicity of an append-only log belies the sophisticated mechanisms required to run it reliably, performantly, and recoverably at scale. Ignoring these operational realities means risking system instability, data loss, and ultimately, a painful, reactive firefighting existence for your operations team. This chapter will delve into the specific operational pitfalls and how to proactively address them. Pitfall 1. Underestimating event store management. The event store is the single, persistent record of your system's history. It's the ultimate source of truth. Underestimating its critical importance and treating it like a casual message queue or a generic database is a significant and common pitfall. Symptoms: performance degradation, slow write throughput, increased latency for appending events, which directly impacts command processing times. Storage exhaustion, rapidly growing disk usage leading to unexpected outage or expensive storage upgrades. Data loss, unrecoverable loss of events due to hardware failure, misconfiguration, or inadequate backup practices. Downtime, the entire system grinds to a halt if the event store becomes unavailable or corrupted. Root cause. This pitfall stems from a lack of specialized knowledge about managing an event store effectively. Wrong tool for the job. Choosing a general-purpose database not optimized for append-only, high-volume writes for your event store. Insufficient sizing. Not accurately planning for disk I/O, network throughput, CPU, and memory requirements proportional to your anticipated event volume and replay needs. Negligent maintenance. Failing to implement regular maintenance routines like compaction to reclaim disk space from deleted streams or events that have passed their retention period. Index rebuilding or monitoring health metrics specific to the chosen event store technology. Inadequate backup strategy. A set-it-and-forget-it mentality or lacking a truly robust plan for backing up the event store, combined with insufficient testing of restoration procedures. Solution: treat your event store as a critical infrastructure component. The event store is the heart of your event source system. Treat it with the care and attention it deserves. Choose wisely. Select an event store technology specifically designed for immutable event streams and high-throughput writes. Options include dedicated event store DB solutions, like EventStoreDB, stream processing platforms, like Apache Kafka, or even specific NoSQL databases, like DynamoDB. When used in an append-only fashion with careful consideration of their consistency models, cloud-managed services can significantly reduce operational burden. Sizing and scaling. Continuously monitor and plan for your event store's capacity. Understand the implications of different storage types, e.g., SSD versus HDD for I/O, network bandwidth, and the specific scaling capabilities of your chosen technology. If using a distributed event store, understand its partitioning and replication strategies. Robust backup and restore. Implement a rigorous and automated backup strategy. This should include both full backups periodically and incremental backups more frequently. Crucially, regularly test your restoration procedures in a non-production environment. A backup is only as good as its ability to restore your data. High availability, HA, and disaster recovery, Dr. Configure your event store for high availability from the outset. This typically involves clustering, replication across multiple nodes, and potentially multi-region deployments to ensure business continuity even in the face of significant failures. Failover mechanisms must be rigorously tested. Pitfall 2. Managing event stream delivery and consumption, the message broker maze. Beyond the event store, the mechanisms for delivering events to and consuming events by projections, sagas, and other downstream services are paramount. Mistakes here can lead to data integrity issues, performance bottlenecks, and system instability. Symptoms: lost events. Events are published but never reach their intended consumers, leading to inconsistent data in read models or unfinished business processes. Duplicate events. Consumers process the same event multiple times, causing incorrect updates, double charges, or erroneous state transitions. Out-of-order events. Events arrive at consumers in an unexpected sequence for a given aggregate stream, leading to incorrect state calculations. Backpressure issues. Consumers cannot keep up with the rate of incoming events, leading to message backlogs, increased latency, and eventually, exhaustion of message broker resources. Root cause. These issues often arise from misunderstanding messaging guarantees. Developers may incorrectly assume exactly once delivery, or strict global ordering regardless of the messaging technology or configuration. Most distributed systems offer, at least once, delivery and ordering guarantees primarily within a single stream partition. Lack of idempotent consumers. Failing to design consumers that can safely process duplicate events without unintended side effects, as discussed in Chapter 4. This is your primary defense against, at least once, delivery. Ignoring consumer lag. Not actively monitoring how far behind consumers are from the latest event in the stream, which indicates stale read models. Poorly designed message routing. Overly complex or inefficient routing and filtering of events to consumers. Solution: build resilient, idempotent consumers and monitor lag. Operationalizing event delivery requires a strong understanding of distributed messaging and consumer design. Embrace idempotency, reinforced. This cannot be stressed enough. Ensure all your event consumers, whether they are projection builders, Saga instances, or external system integrations, are designed to be idempotent. This is your most robust defense against duplicate event deliveries, which are a common occurrence in distributed environments. Understand ordering semantics. Recognize that strict global event ordering is rarely achievable or necessary. Ordering guarantees typically apply per stream, i.e., events belonging to a single aggregate instance arrive at consumers in their correct append order. Leverage this consistent ordering for aggregates, but design cross-aggregate processes, sagas, with eventual consistency in mind. Manage consumer groups. Utilize consumer group patterns, common in technologies like Kafka or Azure Event Hubs, to allow multiple instances of a consumer to process different partitions of an event stream in parallel, enabling horizontal scaling of your read models. Monitor consumer lag. Implement continuous monitoring of consumer lag. The difference between the latest event in the stream and the latest event processed by a given consumer. High lag is a direct indicator of stale data in your projections and potential performance bottlenecks. Alert on this metric. Implement dead letter queues, DLQ. Design your messaging system with dead letter queues. Events that fail processing repeatedly after configured retries should be moved to a DLQ for manual inspection and reprocessing, preventing them from blocking the main processing pipeline. Pitfall 3. Operationalizing projections, rebuilds, and schema changes. As discussed in Chapter 4, projections are materialized views of your event stream. While invaluable, their operational management, especially during schema changes or recovery scenarios, can be complex. Symptoms: long downtimes for read models. When a projection needs to be rebuilt or its schema changed, the application's read functionality might be severely impaired or offline for extended periods. Data integrity issues. Rebuilds fail partway through, leading to corrupted or incomplete read models that cannot be trusted. Resource spikes. Rebuilding large projections can cause sudden, massive spikes in CPU, memory, and database I/O, overwhelming your infrastructure and impacting other services. Root cause: lack of clear strategy for read model evolution. No pre-planned approach for how to roll out schema changes without interruption, as discussed in Chapter 4. Underestimation of rebuild time resources. Failing to calculate or account for the time and compute resources required to replay millions or billions of events for a full historical rebuild. Insufficient tooling. No automated way to kick off, monitor progress, and health check projection rebuilds. Solution: implement robust rebuild strategies and monitor their health. Projections are derived data and are expendable in the sense that they can always be rebuilt from the event store. Leverage this characteristic operationally. Blue-green deployment for read models, reinforced. This is the gold standard for schema evolution. Build the new version of your projection, the green version, fully in the background, updating a separate database or set of tables. Once it's caught up and valid, switch your application's red traffic from the old blue version to the new green version. This enables zero downtime schema changes. Parallel processing for rebuilds. Design your projection rebuild process to leverage parallelism. Partition your event stream and have multiple projection instances. Process different partitions concurrently to significantly reduce rebuild time. Comprehensive progress monitoring. Rebuilds can take hours or days. You need robust instrumentation to track their progress. Number of events processed, total, per second. Estimated time to completion. Any errors encountered during processing. Lag against the live event stream once the historical replay is complete. Capacity planning for spikes. Ensure your infrastructure is provisioned with enough headroom to handle the resource spikes that accompany full projection rebuilds. This might involve temporarily scaling up database instances, adding more message broker consumers, or increasing compute resources for your projection services. Pitfall 4. Comprehensive monitoring and alerting the observability gap. In event sourcing, the traditional black box approach to monitoring, where you only track high-level infrastructure metrics, won't cut it. The internal health of your event streams and consumers is just as critical. Symptoms: unaware of problems. Your team only learns about issues when users start complaining, long after the problem began. Reactive troubleshooting. Debugging becomes a frantic scramble with limited visibility into what's happening. Invisible problems. Data inconsistencies in projections might go unnoticed for days or weeks. Root cause. Missing event sourcing specific KPIs. Focusing only on traditional operational metrics, CPU, memory, disk, network, while neglecting the unique metrics critical to event-driven architectures. Lack of end-to-end tracing. Inability to trace a single command's journey through the various components: command service, aggregate, event store, message broker, projection, saga, to pinpoint latency or errors. No centralized logs. Scattered logs make it impossible to correlate events and understand system behavior. Solution: implement a multi-layered observability strategy. A robust observability strategy is paramount for event sourcing in production. Infrastructure monitoring. Standard metrics for servers, databases, including the event store's underlying hardware and network performance. Event store metrics. Monitor specific metrics of your chosen event store. Write-read latency and throughput. Disk usage and I/O operations. Number of active streams events. Backlog size, if applicable. Consumer metrics, crucial for understanding derived data freshness and health. Consumer lag, the single most important metric for projections and sagas. Is your order summary projection 5 seconds or 5 hours behind? Events processed per second, throughput. Events failed per second, error rate. Retry counts. Active consumer instances. Application metrics. Emit custom metrics from your application code, command processing times and success rates. Number and types of events published. Saga states, e.g., how many order fulfillment sagas are in waiting for payment versus waiting for shipment. Invariant violations or business rule failures. Distributed tracing. Implement distributed tracing across all services. Each command and its resulting events should carry a correlation ID, trace ID/span ID, that propagates through the event store and to all downstream consumers. This allows you to visualize the entire flow, pinpoint bottlenecks, and understand the causal chain of events. Log aggregation and analysis. Centralize all application and infrastructure logs. Ensure logs contain sufficient context, especially correlation IDs, command ID, aggregate ID, trace ID, so you can trace a single operation end-to-end. Use logging levels judiciously. Alerting. Set up thresholds and alerts for all critical metrics. Don't wait for users to report problems. Be actively notified of high consumer lag, unusual error rates, low throughput, or event store health issues. Pitfall 5. Disaster recovery and data correction, the point-in-time predicament. How do you recover when things go seriously wrong in production beyond a simple server restart? What if a bug causes logical data corruption? Event sourcing requires a different mindset for recovery than traditional systems. Symptoms: inability to recover quickly. Your system is down for extended periods after a serious incident, or critical data cannot be rebuilt corrected. Corrupted data. A bug introduces logical inconsistencies, e.g., incorrect customer balances that proliferate through the system. Long recovery times. Restoring a system and rebuilding derived data takes an unacceptably long time. Root cause. Assuming database restore is sufficient. In a traditional database, restoring a backup often means you're back to a consistent state. In event sourcing, restoring the event store to a point in time might resolve infrastructural issues, but it won't fix logical data corruption that was already appended by a buggy process. Lack of forward-fixing strategy. No clear plan for handling logical data errors by issuing compensating actions, commands, rather than trying to edit history. Not leveraging replay. Failing to leverage the deterministic replay capability of the event store for recovery or forensic analysis. Solution: plan for recovery with compensating actions and replay capability. Recovery in event sourcing is about understanding that the event stream is immutable, and correction happens through new events. Read-only backups of event store. Your event store backups are invaluable for recovering the raw event stream itself to a specific point in time. If the event store suffers catastrophic failure, you need to be able to restore it. Ensure you can restore these backups to a new environment for forensic analysis, debugging, or to rebuild all derived read models if necessary. Compensating events commands for logical corruption. For logical data corruption, e.g., a bug caused a customer to be issued incorrect loyalty points, the primary method of correction is not to edit the past. Instead, you analyze the event stream to understand the erroneous state, then issue new compensating commands that result in new events. These new events represent the correction in the immutable ledger, e.g., loyalty points adjusted, customer ID -100. Correction for bug 123. This maintains the integrity of the historical record. Aggregates for forensic data inspection. Leverage your aggregate's ability to reconstruct their state by replaying events. If a specific aggregate instance is suspected of having incorrect data, you can load its stream and step through it, perhaps programmatically or using a debugger tool, to understand its exact state at any arbitrary point in time. This is key for diagnosing issues and planning precise compensating actions. Projection rebuilds for recovery. If a read model projection becomes corrupted, loses data, or needs to be fundamentally restructured, its primary recovery mechanism is a full rebuild from the authoritative event store. This process should be well practiced and monitored, as described in Pitfall 3. Operational playbooks and regular practice. Document clear, step-by-step procedures for common operational scenarios, including disaster recovery, schema changes, and data correction. Crucially, practice these playbooks regularly in non-production environments to identify gaps, refine steps, and build muscle memory within your operations team. Chapter Summary. Event sourcing inherently shifts the focus of operational concerns from mutable database state management to the robust handling of immutable event streams. This paradigm demands specialized operational knowledge, new monitoring techniques, and a distinct approach to recovery. Underestimating the challenges of managing your event store, ensuring reliable event delivery, operationalizing projection rebuilds, establishing comprehensive observability, and planning for complex data recovery scenarios are all common and painful pitfalls. The immutable nature of events means that fixing data is typically done by appending new compensating events, rather than editing history. Proactive planning, strategic investment in appropriate tooling, continuous monitoring of critical event sourcing specific metrics, like consumer lag, and regular practice of recovery playbooks are absolutely essential for successfully bringing an event source system into production and keeping it resilient, performant, and reliable over its entire lifespan. Chapter 8: Performance Pitfalls. When events slow you down. The double-edged sword of scalability. Event sourcing is often championed for its potential to improve scalability. The inherent decoupling of write and read models, the append-only nature of the event store, and the ability to scale processing by adding more event consumers all seem to point towards a naturally performant architecture. However, like any powerful pattern, event sourcing introduces its own set of unique performance challenges. Missteps in design and implementation can quickly turn this seemingly scalable solution into a sluggish beast, characterized by high latency, slow response times, and an insatiable appetite for resources. This chapter will uncover the common performance pitfalls and offer practical strategies to keep your event source system running smoothly. Pitfall 1. Aggregate reconstruction cost. As we learned in Chapter 3, aggregates are the guardians of consistency, safeguarding business invariance. Every time a command is processed, the aggregate must meticulously reconstruct its current state by replaying its entire history of events. While this is conceptually elegant, it can become a significant performance bottleneck for aggregates that accumulate a large number of events over their lifetime. Symptoms: slow command processing. Commands take an unacceptably long time to complete, especially for requests targeting long-lived entities, e.g., a customer account that has existed for years and generated thousands of transactions. High write latency. The system feels sluggish when users initiate actions that trigger aggregate updates. Resource spikes. Replaying massive event streams consumes significant CPU and memory, leading to resource contention on your aggregate hosting services. Root cause. The fundamental root cause is the linear complexity of aggregate reconstruction. If an aggregate has to replay 10,000 events to validate a command, that's 10,000 deserializations, 10,000 method calls, apply, and 10,000 state updates. While each individual operation is fast, their cumulative cost becomes prohibitive for high-volume aggregates. Solution: implement snapshotting for aggregates. The primary solution to mitigate aggregate reconstruction cost is snapshotting. What is a snapshot? An aggregate snapshot is a saved representation of the aggregate's state at a particular point in its history. Instead of replaying all events from the beginning of time, you can instruct the aggregate to load the latest snapshot and then only replay events that occurred after that snapshot. Think of it like saving your game progress in a video game. You don't have to start from the very beginning every time. You load your last save point and continue from there. When to snapshot? Snapshots are typically taken periodically. For example, after every 100 or 500 events, or at significant business milestones, like order confirmed or account closed. The optimal frequency depends on the aggregate's event volume and size. Too frequent, and you incur excessive write overhead. Too infrequent, and you lose much of the performance benefit. Impact. By loading a snapshot, an aggregate might only need to replay a dozen or a few hundred events instead of many thousands, drastically reducing loading time and CPU cycles. Important considerations for snapshotting. Storage. Snapshots need to be stored alongside your event stream or in a separate, highly performant store. Consistency. Snapshots are eventually consistent representations. If a snapshot is taken while an event is in flight, the aggregate will simply receive that event after loading the snapshot, ensuring consistency. Evolution. Like event schemas, snapshot schemas will also evolve. You need a strategy for backward compatibility when loading old snapshots or generating new ones based on an updated aggregate structure. Pitfall 2. Event stream throughput and latency. Events are the lifeblood of your system, constantly flowing from production, writing to the event store, to consumption, by aggregates for reconstruction, and by projections sagas. Bottlenecks in the event stream itself can cripple your entire system. Symptoms: high consumer lag. Projections, sagas, and other event consumers fall increasingly behind the live event stream, leading to very stale read models and delayed business processes. Slow event persistence. Adding new events to the event store becomes sluggish, directly impacting the responsiveness of your command processing. Message broker bottlenecks. Your underlying message broker, if separate from the event store for distribution, struggles to handle the volume and velocity of events. Root cause: inefficient event serialization. If your event payloads are large or the serialization/deserialization process, e.g., to JSON, Avro, protobuf, is inefficient, it will consume excessive CPU cycles and network bandwidth. Network latency. The geographical distance between your producing services, the event store, and various consuming services can introduce significant delays. Event store under-provisioning. The event store itself might not have sufficient I/O performance, CPU, or memory to handle the peak write volume. Too many tiny events, revisited from Chapter 2. A proliferation of very small, overly granular events increases the sheer number of messages to process, creating overhead per event that can accumulate quickly. Solution: optimize serialization, batching, and event store scaling. Ensuring a smooth, high-throughput event stream is vital for overall system performance. Compact event payloads. Design your event payloads to be as lean as possible. Only include the data truly relevant to what happened. Choose efficient serialization formats, e.g., protocol buffers, Avro, or highly optimized JSON libraries over verbose ones. Batching event appends. While events are appended logically one at a time, many event stores and message brokers can benefit from batching multiple events from different aggregates or multiple events from the same aggregate as one transaction into a single write operation. This reduces network round trips and I/O overhead. Scale your event store. Continuously monitor the performance metrics of your event store, as discussed in Chapter 7, and scale vertically, more powerful hardware, or horizontally, more nodes partitions, as needed. Ensure your event store is deployed for optimal I/O, e.g., fast SSDs, dedicated storage networks. Optimize network topology. Minimize network hops and latency between your core services and the event store. Collocate them within the same availability zones or regions where possible. Event aggregation, carefully. While generally you should avoid macro events, in very constrained performance scenarios, you might consider aggregating very frequently occurring, very low business value events into a single batch event at the production boundary, if the loss of individual fidelity is acceptable. This is a highly nuanced decision and should be approached with extreme caution, as it can hide true business events. Pitfall 3. Read model query performance. The beauty of CQRS is that read models are purpose-built for querying. However, poor design or implementation can quickly turn these powerful views into performance bottlenecks themselves. Symptoms: slow UI API responses. User-facing queries or reports take an excessive amount of time to load, leading to a poor user experience. Database overload. The read model database is constantly stressed, experiencing high query times and resource contention. Stale data due to slow queries. Even if the projections are caught up, the queries against the read model are so slow that the data seen by the user is effectively stale by the time it's retrieved. Root cause: poor denormalization. The read model tables are not denormalized enough, requiring complex, costly joins at query time to retrieve information that could have been pre-computed by the projection. Inadequate indexing. Missing or improperly chosen indexes on the read model database prevent efficient data retrieval. Suboptimal database choice. Using a database unsuited for the specific read patterns, e.g., a pure relational database for highly dynamic, schemaless searches. Inefficient projection handlers, revisited from Chapter 4. Latency is introduced because projection handlers are slow to update the read model, leading to large backlogs and high consumer lag. Solution: aggressive denormalization, specialized read models, and correct indexing. Optimizing read models is about making them incredibly fast for specific query patterns. Denormalize aggressively. Denormalization is your best friend for read models. Combine data from multiple sources into a single, flat table optimized for a specific query. Don't worry about data duplication here. That's handled by other read models or can be reconciled. Example: for an order summary read model, instead of storing customer ID and then joining to a customer table, denormalize and store customer name and customer email directly in the order summary table. Purpose-built read models. Don't try to make one read model satisfy all your querying needs. Create multiple, specialized read models, each optimized for a particular query or report. Example: you might have an order summary read model for a dashboard, an order line item details read model for detailed views, and an accounting report read model for financial data. Each is updated by events, but their structure is unique. Index strategically. Analyze your query patterns and create indexes that support them efficiently. Use tools to analyze query plans and identify slow queries, then add or modify indexes accordingly. Choose the right database. Select the read model database technology that best suits your query patterns. Relational databases, good for structured, tabular data with complex filtering. Document databases, NoSQL. Excellent for highly denormalized, nested data optimized for single record retrieval or simple range queries. Search engines, e.g., Elasticsearch, ideal for full-text search, faceted search, and complex analytical queries. Graph databases, useful for network data and relationship queries. Optimize projection handlers. As previously discussed in Chapter 4, ensure your projection handlers are lean and efficient. Batch writes to the read model database to minimize I/O and network overhead. Pitfall 4, disk and storage management, the ever-growing log. The append-only nature of the event store means that data continuously accumulates. Without proper management, this ever-growing log can lead to spiraling storage costs and performance degradation. Symptoms: soaring storage bills. Cloud storage costs become unexpectedly high due to the sheer volume of historical events. Slow backups and restores. The larger the event store, the longer it takes to back up and, more critically, to restore in a disaster recovery scenario. Performance hit on disk I/O. As the event store grows, simple disk operations might become slower if not properly maintained or partitioned. Root cause: infinite retention policy. Storing all events forever, even those that are extremely old, have low replay value, or are not required for legal auditing purposes beyond a certain period. Lack of archival strategy. No process to move older, less frequently accessed events to cheaper, colder storage tiers. Ignoring event stream trimming. Not leveraging the ability of some event stores to trim or tombstone event streams for aggregates that are no longer active, effectively marking the start of their relevant history at a snapshot. Solution: implement intelligent event retention and archival strategies. Manage your historical data actively to control costs and maintain performance. Define retention policies. Work with legal, compliance, and business stakeholders to define clear retention policies for different types of events. Not all events need to be kept online forever. For example, some events might need to be kept for 7 years for compliance, but only the last year's worth needs to be quickly accessible online. Archival to cold storage. Implement automated processes to move older, less frequently accessed events from your high-performance online event store to cheaper, archival storage, e.g., S3 Glacier, Google Cloud Storage Archive. This reduces the active footprint of your event store. Event stream trimming tombstoning. For very long-lived aggregates, once a significant number of events have accumulated and you have a reliable snapshot from Pitfall 1, you might be able to trim the event stream by effectively discarding or marking as unreachable the events that precede the latest snapshot. This essentially reduces the number of events an aggregate needs to replay. This approach requires careful consideration and support from your event store technology, as it's a form of data deletion, albeit a logical one. Ensure you understand its implications thoroughly. Partition your event store. For extremely high-volume systems, consider partitioning your event store. This distributes the load across multiple physical storage units, improving read and write scalability. This can be done by hash of the aggregate ID or by time. Best practices for event sourcing performance. To summarize and ensure your event source system remains performant, integrate these best practices into your design and operations. Aggressive snapshotting for aggregates. Implement snapshots for frequently updated or long-lived aggregates to minimize event replay for command processing. Optimize event payloads and serialization. Keep event payloads lean and use efficient serialization formats and techniques to reduce I/O, network traffic, and CPU load. Batch operations. Leverage batching for appending events to the event store and for updating read models to reduce transactional overhead. Purpose-built read models with denormalization. Design multiple, specialized read models, each aggressively denormalized and optimized for specific query patterns. Use appropriate indexing and database technologies for each. Monitor all layers. Implement comprehensive monitoring across your entire event source stack. Event store, message broker, aggregate services, projection services, and red model databases. Pay close attention to consumer lag as a primary indicator of performance issues. Intelligent data retention. Implement clear policies for event retention and systematically archive older, less frequently accessed events to cheaper storage. Scale appropriately. Continuously evaluate the scaling needs of each component based on current and projected load. Event sourcing components often scale independently, e.g., you might need more read model database capacity than write model capacity. Profile and benchmark. Regularly profile your application and infrastructure to identify performance bottlenecks. Conduct benchmarks under realistic load conditions to uncover issues before they impact production. Chapter summary. While event sourcing offers inherent architectural advantages for scalability, it introduces its own distinct set of performance challenges. High aggregate reconstruction costs, bottlenecks in event stream throughput, inefficient read model queries, and unmanaged disk growth can all lead to a system that struggles under load. The solutions lie in proactively addressing these challenges through strategic design choices like aggregate snapshotting, optimizing event payloads and serialization, aggressively denormalizing data for specialized read models, and implementing intelligent data retention policies. Crucially, a robust monitoring strategy that tracks performance across all layers of your event source system is essential to diagnose and resolve performance issues before they impact your users. By applying these disciplined practices, you can ensure that your event-driven architecture delivers on its promise of being powerful, flexible, and performant. Chapter 9. The When Not to Conundrum. Overengineering with Event Sourcing. The seductive allure of the silver bullet. Throughout this book, we've dissected the inherent complexities of event sourcing, from the nuances of defining clear events to the intricate dance of aggregates, projections, schema evolution, and the operational demands of running such a system. We've explored its powerful capabilities: the crystal-clear audit trail, the ability to time travel through your application's state, the inherent decoupling, and the potential for scalability. It's easy, and perhaps even tempting, to conclude that event sourcing is the ultimate answer to all architectural challenges, a silver bullet for building robust, scalable systems. However, relying on any single architectural pattern as a universal panacea inevitably leads to overengineering, increased complexity, and ultimately, project failure. Event sourcing, despite its undeniable strengths, is no exception. There are indeed scenarios where its implementation introduces more overhead and liabilities than benefits, making simpler, more traditional approaches a far superior choice. This chapter will delve into the critical, when not to question, helping you identify situations where event sourcing might be overengineering. Pitfall 1. Event sourcing for simple CRUD problems, the hammer and nail syndrome. One of the most common misapplications of event sourcing is forcing it onto problems that are fundamentally simple: create, read, update, delete, CRUD operations. Symptoms: excessive complexity for basic features. Implementing a seemingly straightforward feature, e.g., updating a user's profile picture or changing a product description, feels overwhelmingly complex, requiring event definitions, aggregate logic, projection updates, and consideration for schema evolution, whereas a simple database update would suffice. Slow development velocity. The team's productivity appears to plummet. Features that were previously quick to implement now involve lengthy discussions, intricate design work, and a disproportionate amount of code for seemingly minor changes. Developer frustration. Developers constantly question the utility of the pattern for simple tasks, leading to skepticism and reduced morale. Dumb events and aggregates. The events being produced lack any significant business meaning, e.g., user email updated, and the aggregates simply act as data pass-throughs without enforcing any complex invariance or rich behavior. Root cause. This pitfall stems from applying a powerful, specialized tool to a problem that doesn't inherently require its sophistication. Event sourcing comes with a non-trivial inherent overhead: defining events meticulously, as discussed in Chapter 2, designing proper aggregate boundaries, Chapter 3, creating and maintaining projections, Chapter 4, managing schema evolution, Chapter 5, and dealing with increased operational complexity, Chapter 7. For problems that primarily involve storing and retrieving current state without a deep need for historical audit, time travel, or complex domain behavior, this overhead yields diminishing, if not negative, returns. Solution: prioritize simplicity, evaluate true business need. Before instinctively reaching for event sourcing, rigorously assess whether the problem truly benefits from its unique capabilities. Question the need for audit trail. Does the business strictly require a full, immutable historical audit log of every change for regulatory compliance, forensic analysis, or explicit business insight? If simple logging or database change tracking suffices, event sourcing might be overkill. Time travel justification. Is there a proven business need to reconstruct past states or reprocess historical data with new rules? This is a powerful feature, but often a theoretical nice-to-have rather than a critical must-have for simple CRUD. Complex domain behavior. Does the entity undergoing changes possess rich domain behavior with complex state transitions and strict invariants, e.g., a multi-step order fulfillment process, a fraud detection system? If the core logic is merely setting or updating values without deep behavioral rules, a traditional CRUD model likely serves better. For many applications, particularly those focused on managing configuration data, user preferences, or basic content, a standard approach with a relational database might be significantly simpler, faster to develop, and easier to maintain. Pitfall 2. Lack of rich domain behavior, the dumb event trap. Even if a problem isn't purely CRUD, event sourcing might still be a poor fit if the core domain lacks rich behavior or complex business rules. Symptoms. Events are just value changes. Your events consist mostly of X changed to Y or property updated. There's no true business event like order placed or payment received. It's just raw data alterations thinly veiled as events. Aggregates are anemic. Your aggregates act as simple data structures, merely holding values and emitting events without performing significant validation or enforcing complex business logic. They don't represent clear consistency boundaries. Domain logic scattered. Instead of residing within aggregates, most business logic ends up in application services or outside the domain model, processing events rather than being driven by them. Root cause. Event sourcing shines when it models genuine business processes and state transitions. It's fundamentally a behavior-driven pattern. If your domain is primarily about data storage with simple validation rules, and business users don't think in terms of events, e.g., the customer placed an order, but rather data points, e.g., the name field was updated, then the benefits of event sourcing are largely lost. You end up with an event-driven CRUD system, bearing all the overhead without the intrinsic value of capturing meaningful business facts and their derived behavior. Solution. Deeply understand your domain. Let behavior drive choice. The decision to adopt event sourcing should naturally emerge from a rich understanding of your business domain, often facilitated by domain-driven design, DDD, principles. Domain-driven design first. Before choosing event sourcing, invest time in domain modeling. Use techniques like event storming, as mentioned in Chapter 2, to identify true business events, commands, and aggregates. If this exercise yields very few meaningful domain events or complex aggregate behaviors, event sourcing may not be the right fit. Focus on invariance. Does your domain have critical business rules that must always be protected within a single transaction, invariance? If so, event sourcing's aggregate pattern can be very powerful. If invariants are simple, e.g., field cannot be null, traditional validation often suffices. Ubiquitous language test. Do your business users genuinely describe their processes in terms of events, e.g., the customer requested a refund, the item was shipped? If your core conversations are about manipulating records or fields, then event sourcing might be trying to force a square peg into a round hole. Pitfall 3. Over-reliance on future hypothetical needs, the toy problem syndrome. Another common pitfall is adopting event sourcing not for current, concrete needs, but for vague or speculative future requirements that may never fully materialize. Symptoms. What if we need time travel someday? A disproportionate amount of complexity is introduced for features like time travel debugging, historical analytics, or replay capabilities, despite no current or immediate future business need for them. Unused features. The system is built with advanced event sourcing features that developers are proud of, but which are rarely, if ever, utilized by the business. Justification by coolness. The rationale for choosing event sourcing is driven more by technological novelty or perceived elegance than by clear, tangible business value. Root cause. This often stems from a fascination with the cool factor of event sourcing's advanced capabilities, coupled with an inclination to build for speculative future requirements rather than focusing on proven, current business needs. While architectural foresight is valuable, adding significant, immediate complexity for unvalidated future scenarios is a common form of overengineering. Solution: require concrete business justification. Every significant architectural decision, especially one that adds complexity like event sourcing, should have a clear, concrete business justification that outweighs the cost. Prove the need. Before committing to event sourcing, ask, what specific, current business problem does this solve that a simpler approach cannot? Tiered adoption. If a feature like time travel is a future possibility, consider if it can be added later. For example, you can start with an append-only event log, but not full event sourcing across all aggregates, and introduce full aggregate reconstruction and derived projections only when the need demonstrably arises. Build the foundation, but don't build the entire mansion for a hypothetical party. Cost-benefit analysis. Honestly evaluate the known costs of event sourcing, increased development time, operational complexity, learning curve, against the guaranteed benefits for your specific project. Pitfall 4. Team skill set mismatch, the training deficit. Even for problems suitable for event sourcing, the reality of your team's current capabilities can be a significant obstacle. Symptoms: prolonged learning curve. The team takes an inordinate amount of time to grasp core event sourcing concepts, e.g., why aggregates are separate from events, how projections work. High bug rate. Despite effort, the system is plagued by subtle bugs related to concurrency, consistency, and event processing. Low velocity and morale. Development grinds to a crawl, and the team experiences constant frustration due to the inherent complexity and their perceived inability to master it. Ad hoc solutions. Instead of applying the pattern correctly, the team creates workarounds that undermine the benefits of event sourcing. Root cause. Event sourcing, and its closely related patterns like domain-driven design and CQRS, demand a different mental model and a higher level of distributed system understanding compared to traditional application development. Without prior experience, adequate training, and sustained mentoring, teams can easily drown in the cognitive load required to implement it effectively. Solution: assess team readiness and invest in training. Be brutally honest about your team's current readiness and capacity for learning complex new paradigms. Realistic assessment. Conduct a realistic assessment of your team's experience with distributed systems, eventual consistency, and domain modeling. Invest in training and mentoring. If you decide to proceed, commit to significant upfront and ongoing investment in training, workshops, like event storming, and potentially bringing in experienced practitioners to mentor the team. Start small. Don't bet your entire critical new platform on event sourcing if the team is new to it. Start with a non-critical side project or a smaller, isolated subdomain where the impact of early missteps is manageable. Consider a hybrid approach. It's perfectly viable to use event sourcing for only a core, highly behavioral part of your system, while other, simpler parts continue to use traditional CRUD. This allows the team to gain experience gradually without overwhelming them. Pitfall 5, unsuited for highly consistent, low-latency reads writes, the strong consistency trap. While event sourcing has excellent scalability potential for writes, its red side, relying on eventual consistency, might not be suitable for every scenario. Symptoms: business users demand immediate consistency for all data. The primary user-facing interactions require that any change is reflected across all views and reports immediately, globally, and transactionally. Constant pressure to eliminate lag. The team is under continuous pressure to reduce the eventual part of eventual consistency to zero, leading to complex and inefficient polling or forcing distributed transactions that are antithetical to event sourcing. Complex consistency workarounds. Developers implement elaborate schemes to ensure read-your-own rights for every single UI interaction, adding significant overhead. Root cause. This pitfall arises from deliberately or inadvertently choosing event sourcing for a domain where absolute, real-time, strong transactional consistency across all data boundaries is paramount and cannot be relaxed. For example, a stock exchange matching engine or certain financial trading systems might require every single order and trade to be reflected instantly and consistently across all views globally within milliseconds. A scenario where eventual consistency presents significant challenges. Solution: acknowledge trade-offs. Consider hybrid or alternative models. No single architecture perfectly fits all consistency requirements. Embrace trade-offs. Understand that event sourcing trades immediate, global consistency for scalability, auditability, and domain richness. If immediate, strong consistency is a non-negotiable, all-encompassing requirement at every data point, event sourcing might not be the right base technology. Hybrid architecture. It's entirely possible and often practical to mix and match. For parts of your system that demand hard, global transactional consistency, use a traditional database. For the parts that benefit from auditing, temporal querying, and high-throughput writes driven by complex domain behavior, use event sourcing. This allows you to leverage the strengths of each. Revisit requirements. Sometimes, the immediate consistency demand from the business stems from an unexamined assumption. Engage in dialogue to understand the why behind the requirement. Often, eventual consistency within a few seconds is perfectly acceptable if the user experience is managed well, as discussed in Chapter 4. Best practices for when not to. Navigating the when not to is as crucial as understanding how to. Here are some guiding principles. Start simple, CRUD-first mentality. Adopt a mindset where simplicity is the default. Can you solve the problem effectively with traditional CRUD operations and a relational database? Only introduce event sourcing when a clear, compelling business or technical need truly dictates its adoption. Identify specific business value. Always articulate the concrete, tangible business value event sourcing will deliver that a simpler alternative cannot. Avoid adopting it for abstract, scalability, or flexibility without clear use cases. Domain-driven design is key. Before choosing event sourcing, deeply understand your domain. Event storming is an excellent catalyst to reveal if your domain is genuinely event-rich and behavioral or simply data-centric. Embrace hybrid architectures. Event sourcing doesn't have to be an all-or-nothing proposition. Leverage it for the complex, behavior-rich, or highly auditable parts of your system, and use traditional approaches for simpler functionality. This allows you to reap the benefits where they matter most, while minimizing complexity elsewhere. Assess team maturity honestly. Be realistic about your team's current capabilities. If the team is new to distributed systems, DDD, and event sourcing, commit to significant investment in training and mentoring, or defer a full-scale adoption. Question assumptions. Challenge assumptions about consistency requirements. Engage with stakeholders to understand the true business implications of eventual consistency and whether near real-time is sufficient. Chapter summary. Event sourcing is a powerful and valuable architectural pattern, but it is not a universal solution. Applying it to problems that are fundamentally simple CRUD operations, that lack rich domain behavior, or where speculative future needs are the primary justification, leads to significant overengineering and unnecessary complexity. Furthermore, a mismatch with team skills or a fundamental conflict with stringent, global strong consistency requirements can quickly turn its benefits into liabilities. The decision to adopt event sourcing should always be a deliberate, informed choice, based on a clear understanding of its benefits relative to its costs within your specific business domain, project needs, and team capabilities. By rigorously questioning the why and strategically embracing hybrid architectures where appropriate, you can avoid the perils of overengineering and ensure your system is optimally designed for its true purpose, rather than just conforming to a popular architectural trend. Chapter 10, People and Process, Organizational Adoption Challenges. Even with a perfectly designed event sourcing architecture, a robust infrastructure, and meticulous coding practices, the journey to successfully adopting an event-driven paradigm can stumble and fail if the human and organizational elements are overlooked. Event sourcing is not merely a technical pattern. It represents a significant paradigm shift that fundamentally impacts how teams work, communicate, collaborate, and even think about building software. Ignoring these socio-technical challenges is a common and often fatal flaw. This chapter will delve into the organizational and cultural pitfalls that frequently hinder event sourcing adoption and how to navigate them. Pitfall 1: Resistance to new paradigms, the "we've always done it this way" mentality. One of the most immediate and pervasive challenges is the natural human and organizational resistance to change. Teams, both technical and non-technical, are comfortable with established practices, particularly the familiar CRUD, create, read, update, delete approach. Symptoms: skepticism and reluctance. Developers express skepticism about the necessity or benefit of such a complex approach when a simpler database update seems to solve the immediate problem. Business analysts may struggle with the abstract concept of events over direct state manipulation. Forcing old patterns. Teams attempt to squeeze event sourcing into a traditional CRUD mindset, resulting in generic events, like entity changed, and aggregates that don't enforce rich invariants, thereby negating the core benefits while retaining the complexity. Blaming event sourcing for complexity. Any increase in development time, perceived slowness, or unexpected issues are immediately attributed to event sourcing, even if the root cause lies elsewhere, e.g., poor design within the chosen pattern. Reduced morale. As frustration mounts, enthusiasm wanes, leading to lower team morale and productivity. Root cause. This resistance stems from a combination of comfort with existing patterns, a natural human fear of the unknown, an underestimation of the learning curve involved with event sourcing and related concepts like domain-driven design, DDD, and CQRS, and often, a lack of clear vision or sustained leadership in championing the new approach. Solution: education, evangelism, and gradual adoption. Overcoming this resistance requires patience, clear communication, and strategic rollout. Proactive education. Invest heavily in training. Organize workshops, internal presentations, and study groups. Focus on why event sourcing is valuable, revisiting the benefits from Chapter 1, rather than just how it works. Explain the problems it solves and how it fits into the broader architectural vision. Leadership buy-in and communication. Senior technical leaders and product management must clearly articulate the strategic reasons for adopting event sourcing. They need to actively communicate its benefits and signal their commitment to supporting the team through the learning phase. Start small, celebrate wins. Don't attempt a big bang adoption across your entire organization or even a massive new project. Start with a smaller, less critical project, or isolate a core business domain where event sourcing's benefits are most apparent and the risk of failure is manageable. Celebrate every small success, e.g., successful aggregate reconstruction, a working projection, a simplified process flow to build confidence and positive momentum. Showcase success stories. Identify and share examples, both internal and external, of how event sourcing has delivered tangible value, auditability, resilience, flexible analytics in real-world scenarios. Pitfall 2: Siloed thinking and lack of cross-functional collaboration. Event sourcing thrives on a shared understanding of the business domain, transcending traditional functional boundaries. If teams operate in silos, the adoption of event sourcing will falter. Symptoms: business-technical divide. Business analysts define requirements in a way that doesn't map well to events. Developers build event structures that don't reflect true business intent, as discussed in Chapter 2, Pitfall 1. DevOps disconnect. The development team designs complex event streams or operational characteristics, like massive event replay, without consulting the operations team, who then struggle with deployment, monitoring, and recovery, as discussed in Chapter 7. Team optimization over system optimization. Individual development teams optimize their microservices or components in isolation, leading to an inconsistent event model or inefficient overall system behavior. Root cause. This pitfall stems from traditional organizational structures that foster separation, e.g., separate business, development, and operations departments. A lack of shared language, common goals, or a reluctance to step outside one's perceived role can severely impede the cross-functional collaboration vital for event sourcing. Solution: Foster ubiquitous language, event storming, and DevOps culture. Promoting a culture of shared understanding and collaborative ownership is essential. Ubiquitous language, from DDD. Actively cultivate a shared language between business and technical staff. This means using the same terms for concepts, events, and commands. This reduces ambiguity and fosters a common mental model of the domain. Event storming, revisited and emphasized. This collaborative workshop technique, where diverse stakeholders map out business processes by identifying events, commands, and aggregates, is not just a design tool. It's a transformative collaboration tool. It forces business experts, developers, and even operations staff into the same room to build a shared understanding and co-create the event model. This helps prevent dumb events and ensures operational considerations are surfaced early. Adopting DevOps principles, break down the wall between development and operations. Encourage developers to understand the operational implications of their designs, deployment, monitoring, recovery. Empower operations staff to contribute to the design process, providing feedback on operational feasibility and maintainability. Foster shared responsibility for system health. Cross-functional teams. Where possible, organize teams into truly cross-functional units, e.g., a single team responsible for a specific bounded context that include product owners, business analysts, developers, and even embedded operations specialists. Such teams naturally foster collaboration around the entire lifecycle of their domain. Pitfall 3. Inadequate investment in tooling and infrastructure. Event sourcing introduces new infrastructure components and operational needs that often go unbudgeted or are underestimated. Symptoms: manual operational processes. Teams resort to manual processes for event schema evolution, Chapter 5, projection rebuilds, Chapter 4, or data correction, Chapter 7, leading to long downtimes and human error. Lack of ease-specific monitoring. Traditional monitoring tools fail to provide insights into critical event sourcing metrics like consumer lag or event store health. Reinventing the wheel. Teams spend excessive time building custom tools for event replay, schema management, or operational dashboards instead of leveraging or adapting existing solutions. Works on my machine, but not in production. The absence of proper infrastructure for reliable event delivery, storage, and processing leads to inconsistencies and failures in production. Root cause. This pitfall stems from an underestimation of the true operational complexity, as thoroughly explored in Chapter 7, often coupled with budget constraints or a lack of awareness regarding the specialized tooling available for event sourcing ecosystems. Solution: budget for tools, build a platform team, prioritize automation. Treat event sourcing infrastructure as a first-class citizen. Dedicated budget. Allocate specific budget for event sourcing platforms and tooling beyond just application development. This includes the event store, message brokers, schema registries, monitoring solutions, and potentially third-party libraries or frameworks that simplify ease implementation. Event sourcing platform team. For larger organizations, consider establishing a dedicated platform or enablement team. This team's mission is to provide the underlying infrastructure, standardized libraries, best practices, and support for all event sourcing initiatives, thereby empowering individual development teams. This prevents duplication of effort and ensures consistency. Prioritize automation. Automate every repeatable process. Deployment pipelines for event source services, projection rebuilds, event stream replays for testing, and monitoring setup. This reduces manual errors, accelerates development cycles, and frees up engineers for more valuable work. Pitfall 4. Resistance to change in testing and debugging approaches. Event sourcing demands a different mental model for testing and debugging than traditional state-based systems. If teams cling to old habits, productivity will suffer. Symptoms: clinging to database-centric tests. Development teams continue to design integration tests that primarily assert against the state of a relational database, struggling to adapt to event-driven behavioral testing. Frustration with temporal debugging. Developers find it difficult to debug by examining event streams and time traveling, preferring to inspect the current state, which often provides insufficient context. Inability to reproduce bugs. Without effective event replay or behavioral testing practices, bugs become elusive and hard to fix, leading to long resolution times. Root cause: human habit and comfort with familiar tools. A lack of specialized training on event-driven testing techniques, like the given-when-then pattern discussed in Chapter 6, and the practical skills for temporal debugging. Solution: mentorship, dedicated training, and practical examples. Help teams transition by providing the necessary support and demonstrating effective new approaches. Hands-on training and mentorship. Provide immersive, hands-on training sessions focusing specifically on event-driven testing and debugging. Pair experienced event sourcing practitioners with less experienced team members to demonstrate these techniques in real time. Showcase successes. Actively highlight and celebrate instances where new testing or debugging approaches led to efficient bug reproduction and quick fixes. This provides tangible proof of their value. Tooling for debugging testing. Ensure the team has access to and training on tools that facilitate event stream analysis, historical replay, and aggregate state reconstruction. Make the temporal labyrinth traversable. Pitfall 5. Managing expectation of instantaneous data, the business buy-in challenge. Despite its power, event sourcing introduces eventual consistency to many read models. If this trade-off is not properly managed with business stakeholders, it can lead to constant friction. Symptoms: non-negotiable demands for immediate consistency. Business users consistently demand that all data reflect changes instantaneously, even for read models where eventual consistency is inherent. Pressure to eliminate lag. The development team is under continuous pressure to reduce any perceived lag in projections to zero, leading to inefficient and complex solutions that undermine the benefits of event sourcing. User frustration with UI. Users become frustrated when an action they just performed doesn't immediately appear updated in their view. Root cause. This pitfall largely results from a failure to transparently communicate the implications of eventual consistency early in the architectural and design phases. It can also stem from a technical team that overpromises or fails to involve product owners sufficiently in key architectural decisions. Solution: transparent communication, user experience design, and phased feature rollout. Effective management of expectations is crucial for business buy-in and user satisfaction. Preemptive communication. From the very beginning of an event sourcing project, educate business stakeholders about the concept of eventual consistency and its impact on the user experience. Revisit Chapter 4, Pitfall 1. Clearly articulate the trade-offs. What you gain: auditability, scalability, domain richness by accepting eventual consistency. Design for managed expectations. Implement UI/UX patterns that manage user expectations about data freshness. This includes immediate feedback, confirming a successful command immediately, e.g., order placed successfully. Loading indicators. Showing clear loading or processing indicators until the relevant read model is updated. Notifications. Delivering asynchronous notifications, e.g., email, in-app alerts, when an operation is fully confirmed and reflected everywhere. Strategic feature rollout. When introducing event sourcing, start with less critical features or parts of the system where the eventual consistency model is more easily tolerated by the business. This provides a gradual learning curve for users and business stakeholders. Chapter summary. Event sourcing success is not solely a technical endeavor. It is a socio-technical transformation that requires significant adaptation from people and processes within an organization. Resistance to new paradigms, siloed thinking, inadequate investment in tooling, clinging to old testing habits, and mismanaged expectations regarding data consistency are all common pitfalls that can derail an otherwise well-designed system. Overcoming these challenges requires proactive education, strong leadership buy-in, fostering a culture of cross-functional collaboration, especially through domain-driven design and event storming, strategic investment in specialized tooling and automation, and a patient, transparent approach to managing business expectations. By focusing as much on the human element and organizational processes as on the code itself, you can successfully navigate the complexities of event sourcing adoption and truly unlock its long-term benefits of flexibility, resilience, and deep domain understanding. Chapter 11, Repairing the Damage, Recovery Strategies and Best Practices. The inevitability of damage. Even the most thoughtfully designed and meticulously implemented systems will eventually encounter problems. Networks fail, hardware wears out, software can have subtle bugs, and sometimes human error plays a part. When these incidents occur in an event source system, the approach to recovery and repair fundamentally shifts due to the core principle of event immutability. Unlike traditional databases, where you might directly edit or delete erroneous data, event sourcing requires a different mindset rooted in understanding causation rather than merely correcting state. This chapter will delve into the critical strategies for recovering from failures and repairing damage in an event-sourced landscape. It's not just about getting back online. It's about leveraging the unique properties of event sourcing to understand what went wrong, ensure historical integrity, and proactively prevent future issues. Pitfall 1. Attempting to mutate history, the forbidden edit. The most tempting, yet fundamentally flawed, pitfall in event sourcing recovery is the instinct to directly modify or delete events in the event store. Symptoms: direct database operations. Operations teams or developers, accustomed to traditional database management, attempt to log into the event store's underlying database and issue delete or update commands on event records to fix a mistake or remove erroneous data. Loss of audit trail. If history is directly altered, the true sequence of events is obscured, compromising the system's auditability, its ability to replay and reconstruct past states, and undermining confidence in the integrity of the data. Widespread inconsistencies. Downstream systems, projections, sagas, external integrations that have already processed the forbidden event will remain in an inconsistent state unless they are also manually corrected. A complex and error-prone process. Root cause. This pitfall stems from a deep-seated misunderstanding or outright disregard for the core principle of event immutability. The ingrained CRUD, create, read, update, delete mindset, where data can be freely altered, clashes directly with the append-only nature of the event store. Solution: compensating events and commands. The unwavering rule in event sourcing is, history cannot be changed. Correction happens forward by appending new events. Identify and analyze. When an error occurs, e.g., a customer was incorrectly charged or a product status was wrongly updated, the first step is forensic analysis. Use the event stream to precisely understand the sequence of events that led to the erroneous state. This often ties into the debugging techniques discussed in Chapter 6. New commands, new events. Once the error is understood and the desired correct state is determined, you issue new commands to the system. These commands are specifically designed to reverse the effects of the erroneous event or to bring the aggregate to its correct state. These new commands then trigger compensating events. Example: if a customer was accidentally charged $50, you don't delete the customer charged $50 event. Instead, you issue a refund customer $50 command. This command, processed by the appropriate aggregate, will emit a new event like customer refunded $50. Example: if a product was wrongly marked out of stock, you don't mutate the product out of stock event. You issue a revert product status to previously available command, which emits a product stock availability reverted event. Rationale: this approach maintains the complete, immutable audit trail. The event stream now contains both the original erroneous event and the subsequent compensating event, clearly showing the full chronological story, including the correction. All downstream systems that monitor the event stream will naturally receive and process the compensating event, bringing themselves into consistency without manual intervention. Analogy: think of a bank statement. If a fraudulent transaction occurs, the bank doesn't erase it from your statement. Instead, they add a new entry for a chargeback or a reversal, clearly showing that the original transaction happened and then was later corrected. Your statement remains a complete, auditable record. Event sourcing functions on the same principle. Pitfall 2: disregarding point-in-time recovery and forensic analysis. While you don't modify the event store for logical corrections, you absolutely must be able to restore it for infrastructure failures or to perform deep historical analysis. Neglecting this is a significant recovery pitfall. Symptoms: inability to restore to a specific point. After a catastrophic event store failure, you can only restore to the last full backup, potentially losing recent events or causing a large data gap. Difficulty diagnosing complex issues. When a bug or data inconsistency appears, you cannot easily rewind your application to an exact moment in time to understand its state or to replay the exact sequence of events that led to the problem. Prolonged outages. System-wide recovery takes excessively long because there's no clear strategy for using the event log for recovery beyond simple database restore. Root cause. A lack of understanding of how to fully leverage the event log for sophisticated recovery scenarios, coupled with inadequate tooling and processes for managing historical rebuilds and forensic analysis. Solution: embracing replay for recovery and forensics. The immutable event log is your greatest asset for recovery. Learn to leverage its deterministic replay capability. Robust, testable backups of the event store. As elaborated in Chapter 7, implement a tiered backup strategy, full, incremental, for your event store based on your recovery point objective, RPO. Crucially, regularly test your restoration procedures in a non-production environment. A backup that cannot be restored is useless. Targeted replay for specific aggregates. For logical corruption affecting a single aggregate instance, you don't need to replay the entire system. Tools or custom scripts can allow you to replay only that aggregate's specific event stream on a diagnostic instance to reconstruct its state at any point in time and confirm the impact of proposed compensating actions. Full system replay for disaster recovery. For catastrophic data center failures or widespread data corruption, the ultimate recovery mechanism is a full replay of the entire event stream to reconstruct all aggregates and projections onto completely new infrastructure. This is your event sourcing, restore from scratch button and should be practiced. Forensic and diagnostic playbacks. The event stream is a perfect forensic tool. By replaying events step by step, perhaps using a debugger or specialized tooling, you can precisely trace a command's journey, observe aggregate state transitions, and understand how a particular error slipped through. This helps isolate root causes and formulate accurate compensating events. Importance of correlation IDs. Ensure all events contain crucial metadata like correlation IDs, linking events to a command, causation IDs, linking events to the event that caused them, and trace IDs. These identifiers are invaluable during complex recovery and forensic analysis, allowing you to easily filter and group related events from a massive stream. Pitfall 3. Suboptimal projection rebuild strategies. Recovery bottleneck. Projections are derived data. If they get out of sync or become corrupted, they need to be rebuilt. This process, if mishandled, can become a major recovery bottleneck. Symptoms: weeks-long recovery times. After a projection database becomes corrupted or needs a significant schema change, rebuilding it from the event store takes an unacceptably long time, leading to extended periods of impaired or offline read models. Continuous staleness. Projections cannot catch up to the live event stream, resulting in persistently stale user-facing data. Resource exhaustion during rebuilds. The reconstruction process consumes an overwhelming amount of CPU, memory, and database I/O, impacting other critical services. Root cause: inefficient rebuild mechanisms, a lack of parallelism in event processing, not effectively leveraging snapshots, or a failure to plan for the sheer volume of events that need to be replayed. Solution: prioritize fast, parallel, and automated rebuilds. Your strategy for rebuilding projections is critical for operational resilience. Blue-green deployments for read models, reinforced. As discussed in Chapters 4 and 7, this is the gold standard for achieving zero downtime schema evolution and rebuilds. A new instance of the projection is built on separate infrastructure, caught up to the live stream, and then traffic is seamlessly switched. Parallel processing for rebuilds. Design your projection rebuild process to distribute the workload. Partition your event stream, e.g., by aggregate ID, and have multiple, independent instances of your projection consumer process different partitions concurrently. This significantly reduces overall rebuild time. Leverage read model snapshots strategically. For projections that reconstruct a massive amount of data, periodically save snapshots of the read model state. When rebuilding, you can then start from the latest read model snapshot and apply events only from that point forward, instead of replaying the entire stream from the beginning of time. This can drastically cut down rebuild duration. Automated tooling and monitoring. Provide robust, automated scripts and dashboards to initiate, monitor the progress of, and manage projection rebuild processes. Include metrics like events processed per second, total events remaining, estimated time to completion, and any processing errors. Capacity planning for spikes. Always provision your infrastructure with enough headroom to handle the significant resource spikes that accompany full projection rebuilds. This might involve temporarily scaling up database instances, adding more message broker consumers, or increasing compute resources for your projection services during a rebuild. Pitfall 4. Neglecting monitoring and alerting for timely intervention. Even the most robust recovery strategies are reactive. Proactive monitoring and timely alerting are crucial for detecting and addressing problems before they escalate or significantly impact users. Symptoms: problem discovery via user complaints. Your team learns about system issues only when users start complaining, long after the problem has been brewing. Hidden data inconsistencies. Projections might contain subtly incorrect data for days or weeks without being noticed, leading to erroneous business decisions or user dissatisfaction. Chaotic troubleshooting. When an issue arises, there's a frantic scramble due to limited visibility into the health and flow of events. Root cause. An inadequate observability strategy that fails to account for the unique characteristics of event sourcing, focusing only on traditional infrastructure metrics while ignoring the critical key performance indicators. KPIs, specific to event-driven architectures. Solution: comprehensive event-specific monitoring, recap from Chapter 7. A multi-layered and event-specific observability strategy is paramount for event sourcing in production. Consumer lag, the essential metric. This is arguably the most critical operational metric for any event sourcing system. Monitor the lag for every projection and saga, the difference between the head of the event stream and the latest event processed by that consumer. Alert when lag exceeds predefined thresholds, as it indicates stale data in your read models or stalled business processes. Event store health. Monitor the performance and health of your chosen event store technology. Key metrics include write and read latency, throughput, disk usage, I/O operations per second, and network traffic. Set up alerts for any deviations from baseline. Event processing errors. Track error rates within your event handlers for aggregates, projections, and sagas. Identify transient errors, which might self-correct on retry versus persistent errors that require intervention. Saga state tracking. For long-running business processes coordinated by sagas, monitor their state. Identify stuck or dead sagas that are not progressing as expected, as these indicate stalled business processes. End-to-end distributed tracing. Implement distributed tracing across all services involved in your event flow. Ensure that commands and events carry correlation IDs so you can instantly visualize the entire journey of a transaction, from its initiation through all its resulting events, aggregate updates, and projection changes. This is invaluable for pinpointing latency and error sources. Log aggregation and analysis. Centralize all application and infrastructure logs. Crucially, ensure logs contain sufficient context, especially correlation IDs, command ID, aggregate ID, trace ID, so you can effectively trace a single operation end-to-end through numerous microservices. Pitfall 5. Inadequate communication and playbook practice. Even with the best tools and deepest understanding, incidents can become chaotic if teams don't have clear procedures and practiced responses. Symptoms: confusion during incidents. When an issue strikes, team members are unclear about their roles, responsibilities, or the precise steps to take. Prolonged resolution times. Due to disorganization and lack of clarity, Incident resolution takes significantly longer than necessary, increasing downtime and business impact. Repeat failures. Lessons learned from past incidents are not documented or effectively communicated, leading to recurrence of similar problems. Root cause: lack of clear, documented incident response procedures, absence of regular practice drills, and poor cross-functional communication both during and after an incident. Solution: build and practice incident response playbooks. Effective incident management in event sourcing, like any complex system, relies on preparation and practice. Document clear procedures, playbooks. For every common failure scenario you can anticipate, e.g., event store outage, specific projection corruption, logical data errors due to a released bug. Create detailed, step-by-step playbooks. These procedures should outline detection methods, diagnostic steps, resolution actions, and verification steps. Define clear roles and responsibilities. Establish who is responsible for what during an incident. This includes incident commanders, technical leads, communication leads, etc. Everyone should know their role immediately. Regular practice, game days drills. The most effective way to validate your playbooks and train your team is through regular game days or simulated incident drills. Conduct these in non-production environments. Deliberately inject failures, e.g., kill a service, corrupt a projection, introduce high network latency, and observe your team's response. This identifies gaps in documentation, tooling, and team knowledge, building muscle memory and confidence. Conduct blameless postmortems and document learnings. After every incident, whether major or minor, conduct a blameless postmortem. Focus on understanding what went wrong, root cause analysis, what was learned, effective responses, gaps in knowledge tooling, and what changes technical, process, human, are needed to prevent recurrence. Document these findings in a knowledge base accessible to all relevant teams. Robust communication protocols. Establish clear communication plans for incidents. Define who needs to be informed, how often, and what information needs to be conveyed, e.g., internal technical updates, business stakeholder updates, external customer communications. Chapter summary. While event sourcing offers powerful capabilities for building resilient systems, damage and failures are an inevitable part of operating complex software. The unique, immutable nature of events demands a distinct approach to recovery and repair. Attempting to mutate history is a critical error. Instead, logical corrections are made by appending new, compensating events. Leveraging the event stores deterministic replay capability for comprehensive recovery and forensic analysis is paramount. Operational excellence in event sourcing relies on prioritizing fast, parallel projection rebuilds, often via blue-green deployments. Implementing a comprehensive monitoring strategy that focuses on event-specific metrics like consumer lag. And, critically, investing in organizational preparedness through documented playbooks, regular practice drills, and a culture of continuous learning from failures. By embracing these unique aspects of event sourcing, you can transform inevitable incidents into opportunities for growth, ensuring your system remains robust, reliable, and ultimately trustworthy over its entire lifespan. Chapter 12. The Future of Event Sourcing and Continuous Learning. The journey so far. Embracing complexity for resilience. We've journeyed through the intricate landscape of event sourcing, from its compelling promise of auditability and temporal power to the myriad pitfalls that can transform its elegance into a bewildering complexity. We've dissected common mistakes in event definition, aggregate design, projection management, and event schema evolution. We've grappled with the operational realities of deployment, monitoring, and recovery, acknowledging that running an event-sourced system in production demands a refined operational discipline. And crucially, we've explored the when not to conundrum, emphasizing that event sourcing is a powerful tool, not a universal panacea, and its adoption critically depends on the precise problem, project context, and team capabilities. Finally, we've touched upon the human and organizational aspects, recognizing that true transformation requires a shift in mindset and a commitment to cross-functional collaboration. The overarching theme has been clear. Event sourcing, when done right, is a transformative pattern that delivers exceptional flexibility, resilience, and a deep understanding of your business domain. But doing it right means confronting and mastering its inherent complexities, not shying away from them. This book has aimed to illuminate those complexities, expose the common errors, and provide actionable strategies to navigate the temporal labyrinth successfully. Key takeaways: pillars of successful event sourcing. As a summary of our collective learnings, successful event sourcing hinges on several foundational pillars. Mindset shift: move beyond static state thinking. Embrace the narrative of what has happened as the ultimate source of truth. Your data is a flowing, chronological ledger, not a set of mutable records. Deep domain modeling: invest heavily in understanding your business domain. Use collaborative techniques like event storming to discover true domain events, commands, and coherent aggregate boundaries. This is the bedrock of a meaningful event model. Immutability and evolution: respect the immutable nature of events. History cannot be changed. Corrections happen by appending new, compensating events. Plan for event schema evolution proactively by adopting additive changes and employing robust upcasting mechanisms. Dual nature, CQRS. Embrace the separation of your write model, aggregates, and event store from your read model's projections. Understand and manage the implications of eventual consistency and design client experiences that gracefully handle transient data staleness. Operational discipline: the event store is your crown jewel. Treat its management, backup, and recovery with utmost care. Invest in robust, event-specific monitoring, especially consumer lag, and automate projection rebuilds. People and process: event sourcing is not just code, it's a way of working. Foster a culture of learning, cross-functional collaboration, and effective communication. Be transparent about complexities and manage expectations with stakeholders. Pragmatism: event sourcing is a potent hammer, but not every problem is a nail. Be judicious in its application. Consider hybrid architectures and always strive for the simplest viable solution that meets your proven business needs. The evolving landscape of event sourcing: the world of software development is in constant flux, and event sourcing is no exception. While its core principles remain stable, the tools, patterns, and contexts in which it's applied are continuously evolving. Maturing tooling and frameworks: the early days of event sourcing often involved significant bespoke development. Today, the ecosystem is far more mature, with robust, performant, and often cloud-native event stores, message brokers, and development frameworks that reduce the barrier to entry and simplify operational overhead. We can expect this trend to continue, making it easier to build and manage event source systems. Enhanced observability: as distributed systems become the norm, the need for deep observability intensifies. We're seeing more sophisticated tools for distributed tracing, event stream monitoring, and real-time analytics that provide invaluable insights into the flow of events and the health of event-driven architectures. Cloud-native and serverless integration: cloud providers offer managed services for message queuing, streaming, and specialized databases, abstracting away much of the infrastructure management. Serverless functions are increasingly being used as reactive consumers of event streams, further simplifying deployment and scaling of projections and sagas. Emergence of data meshes: event sourcing naturally aligns with data mesh principles, where domain-oriented teams own their data products, including event streams, and make them discoverable and consumable by others. Events are fundamental building blocks for interoperable data products in a decentralized data architecture. Advanced analytics and machine learning: the immutable, historical nature of event streams makes them a perfect source for advanced analytics, business intelligence, and building feature stores for machine learning models. Events provide a rich, untainted record of system behavior for training and analysis. Standardization efforts: while still nascent, there's growing interest in standardizing event formats and protocols, which would further enhance interoperability between different systems and organizations. Embracing continuous learning: despite the increasing maturity of tools and patterns, event sourcing remains a challenging domain. It demands a different way of thinking and a commitment to lifelong learning. The specific pitfalls and solutions discussed in this book provide a strong foundation, but they are not exhaustive, nor are they static. Stay curious, the landscape will continue to evolve. New challenges will emerge, and new solutions will be discovered. Maintain a curious mind and actively seek out new knowledge. Engage with the community. The event sourcing community is vibrant and collaborative. Participate in forums, attend conferences, contribute to open-source projects. Share your experiences and learn from others' successes and failures. Experiment and iterate. Don't be afraid to experiment with new patterns or tools in a controlled environment. Build prototypes, learn from them, and iterate. This practical experience is invaluable. Learn from failures blamelessly. As Chapter 11 emphasized, incidents are inevitable. What truly matters is how your team responds, learns, and adapts. Adopt a blameless culture around postmortems so that every failure becomes a learning opportunity that strengthens the system and the team. Context is king. Remember that no two systems are exactly alike. The true art of architecture lies in understanding your specific context, your business needs, team capabilities, existing infrastructure, and resource constraints, and applying the right patterns pragmatically. Concluding thoughts. Event sourcing is more than an architectural pattern. It's a philosophical approach to system design, rooted in capturing the narrative of your business. It asks you to think in terms of facts and causality, to prioritize history, and to build systems that are inherently observable, auditable, and resilient. This power, however, comes with a learning curve and a set of unique challenges that demand respect and careful consideration. By understanding the common pitfalls, embracing a disciplined approach to modeling and implementation, and fostering a culture of continuous learning and adaptation, you can harness the full potential of event sourcing. May your event streams flow reliably, your aggregates guard their invariance, and your systems serve as clear, trustworthy reflections of your business's journey.